Okay, I think we might get started actually. A couple of minutes early, but we have a packed agenda, so it's good to give us a little bit of breathing space, I think, in the timeline. So I'm Liz Bentley, I'm Chief Executive at the Royal Meteorological Society, and delighted to welcome you all here today to the Geological Society for this joint event between the Royal Met Society and the British Hydrological Society. The meeting is on Forecast to Action, Advancing Flash Flood Resilience. So I'm just doing a welcome. I've got a few minutes really to go through a little bit of admin, a little bit about the work of the Royal Met Society, and a slide as well around the British Hydrological Society. So admin-wise, if there's any issues, you need any first aid, please come and have a chat with either myself or Kat. Kat, can you just stand up? You probably would have seen Kat at the registration desk. Please just come and see one of us if you need any assistance. And we're not expecting a fire drill today, so if we hear the alarms, it is for real and we need to evacuate the buildings. So we have two evacuation points, three actually in here, two at the back and one at the front here, and we'll be guided round to the assembly point outside the building. So the programme, as I mentioned, quite a busy programme today. We have 3 sessions, one this morning before lunch on forecasting warnings and decision making. Lunch will take place in the library where we just had tea and coffee this morning. And then we have 2 sessions this afternoon with the refreshment break in the middle and a panel discussion at the end. So I've got a short video now, that's about 1 minute, just short of 1 minute, about the work of the Royal Meteorological Society. So I'm hoping.
So many conversations start with the weather, and so many answers yet to be found. But it's when you make a connection, a physical connection, a scientific connection, a connection of interest, that's when the world can change and doors can open. Weather doesn't discriminate, and neither do we. There's really no greater time to unite in our passion for understanding weather and climate and shaping the future of our world for the benefit of science and humanity. We may be over 170 years old, but we are not standing still. Our journal showcases the latest advances whilst drawing the past, and our members are some of the most forward-thinking people on the planet. We are an independent voice uniting communities. We connect students with mentors, climate scientists with ecologists, communicators with researchers, and photographers with meteorologists, and we connect everyone with the weather. Whether you are working in world weather or climate, or just have a curiosity about the world around you, we are here. Join us in empowering future generations. Join us to learn something new. Join us on your career journey. Join us in our passion. Join us.
So yes, join us. If you're not a member of the Royal Met Society, there are a few activities listed on here, the kind of work that we do. So like many learned and professional bodies, we publish, we have a portfolio of scientific journals. So we have 8 international journals and other publications that go alongside that as well. We deliver a lot of training and learning. So we have a masterclass series that runs twice a year. We also deliver training, climate change communication training, for example. We do mentoring, we have events such as this one. We're a part of a community of over 3,000 members. We also oversee the professional accreditation in meteorology, so people who want to work for, say, the chartered meteorologist. And people get involved with the society in lots of different ways, either as members but also as volunteers to help us deliver on our mission to advance the understanding of weather and climate for the benefit of everybody. I have a slide here about the British Hydrological Society. So you can see their mission statement to encourage interest, scholarship and good practice in scientific and applied aspects of hydrology, and also to foster involvement in national and international hydrology. They also run events, conferences and webinars, and it's great that we've managed to get this joint event together. I've been talking about it for a little while now. They also offer travel grants to conferences. You can see the breakdown on this slide. They have a studentship award scheme, so they provide funding for people working towards masters. And they have a quarterly magazine as well, with news and updates for the hydrological community. So Happy if you want to come and have a chat during the lunch or the afternoon break with myself, or probably Will, I guess, from the British Hydrological Society, if you want interested in finding out more about either organisation. Okay, so I'm now going to hand over to Linda Spate, who is chairing the first session. So Linda, if you want to come forward, and I'm hoping the slides will magically sort themselves.
Great. Good morning, everyone. I'm really excited to be here today. Flood forecasting and warning is a field that I've been working in since kind of 2012-ish, and it's really great that we've got this joint meeting today to see kind of advances in the kind of research and operational side of the field. So I don't want to chat too much because I've been told lots of times we're tight for time this morning. So we've got 3 great speakers in this session covering UK perspectives and international developments in flash flood forecasting and warning. So firstly, I'd like to invite Stephen Kosher from the Met Office and the Flood Forecasting Centre up to give our first talk. Now, I've got some cards, so if you see me holding them up, you've got 5 minutes and 1 minute left, okay? So the speakers have all got 20 minutes, and then we'll have 10 minutes for question and answers, so get your thinking caps on for some questions.
Smashing, thank you very much. Right, good morning, everybody. Lots to say in 20 minutes, but just to give you a bit of my background, I am both a forecaster and a hydrometeorologist within the Flood Forecasting Centre and the Met Office. So I'm a real practical user of everything of which I'm about to show you here, and all of the work which has been done here, all the scientific background work has been done by a team of people, and this is just a few of the people that I need to thank here. So what I'm going to talk to you about here today, I'm going to talk to you about the warnings and the guidance that the Met Office and Flood Forecasting Centre issued, then have a look at some of the tools of which we use before an event, and then look at some of the tools which we use through events. So what we're trying to forecast is things like this when we have flash flooding. This is a recent example in Coverack in 2017. You can see the overland flow there. And we communicate this out through a couple of products. The Met Office obviously issued the National Severe Weather Warning Service, which you will hopefully all be aware of. And the FFC, the Flood Forecasting Centre, issued the flood guidance statement on the right here, and Adrian, the next speaker, is going to give you a little bit more information about that in a minute. But this is what we're trying to be, we're going to be producing in the pre-event scenario. So the main tool, one of the main tools of which we have in a recent development is the Surface Water Flood Hazard Impact Model, or SWIVM for short. This is what we use in addition to more traditional techniques of looking at tephigrams and looking at broad scale meteorology and things like that. So this utilises UKCEH's, so that's the UK Centre for Ecology and Hydrology, their grid-to-grid model. And the grid-to-grid model is a gridded distributed hydrology model. And within that, it's got its rivers, but one element of that it has is the surface runoff. So we run an ensemble of grid-to-grid models. We run 12 members of that ensemble. And for each grid point, we'll be taking our surface runoff. We will compare that surface runoff to a pre-calculated impact library and say, if we have this amount of surface water of this depth and this velocity in each of these grid squares on our pre-calculated impact library, then what's the risk of surface water flooding? And that's the final output in here. And we do that across our 12-member ensemble, and then we upscale that to our more county outputs, which gives us a risk of surface water flooding on the right-hand side here. So how's that calculated in a bit more detail? We've got an Ordnance Survey map here, and the different shades of blue are the potential depths of water of which we could be having across each grid square. And that's done at an ultra high resolution, as what you can see. It's from the Environment Agency's flood map, well, risk of surface water flooding flood map, which runs at a 2 resolution model. And then you can see that there's a few sites of interest here. On the right hand side here, we've got a fairly urban area, and the water could be, because it has the dark shading here, can be fairly deep. And then we've also got a few more interesting where, you know, some more less deep water could be crossing some roads, but you can see that a lot of the area is actually fairly deep over parkland. So for each of those grid squares, we are assigning those with a risk of, if that was, you know, if this was, if those sites had surface water flooding in them, what would the risk potentially be? So where we've got our urban area here, when we've got fairly deep water, if that has surface water flooding in that area, that would be a severe impact. Where if we had flooding of some parkland, it is obviously, well, no impact whatsoever, really, and everywhere in between that. So what do? We take our grid-to-grid runoff model, and we're making that into a scenario. We're then comparing those scenarios to that pre-calibrated impact library. And we're doing that on a 1 kilometre level, because that's the resolution of grid-to-grid. And then we're doing that across a number of ensemble members, those 12 ensemble members, so that we can essentially look on a county level and see how many members are flagging up a risk of surface water flooding. So this has been a fairly new and emerging science, and it's a tool that we've been using for probably the last 5 to 10 years now, and we're putting further developments into it all the time. Yeah, so that's one of the main tools of which we're using. Obviously, within this area at the moment as well, the question of which I'm going to anticipate from everyone around the room is, what about AI and machine learning? How good is it? And we have done quite a bit of work in this field already. The problem with machine learning is obviously about the data of which the machine is able to learn from. And the Flood Forecasting Centre actually has a really good impact library down to a county level basis. And we've assessed whether the flooding is from surface water or rivers, etc. But actually, we've probably got about 12, 13 years, I'm guessing at that number, of data in there. And at the moment, it's just not enough for the AI models to really be able to have a good understanding about what the risk of flooding is. There's not enough events per county to learn from. So we've had to scale up into more broader areas, looking at, you know, these traditional Environment Agency areas of like Thames, Wales, Anglia. And then you can see that the probability of detection from these events is around about the 70 to 80% risk of detection and risk of no impacts being detected correctly. So it's an area that we're looking at, but overall, we need more data. So I guess the next thing we're going to be thinking about doing is thinking about whether we can be using some proxies for surface water flooding impacts, whether we can hook into partners in the AA and look at car breakdowns, or whether we can look at maybe urban flood alerts from the Environment Agency and see whether we can use those as a proxy. But still, obviously, an emerging science in that area. Right, then after that, we get into the mid-event. So we've put out our National Severe Weather Warning Service, and we're now, you know, we've got convection firing and showers forming. Now, NWP is fantastic at giving us a sense, but in the really short term, that less than 2 hour period, actually nowcasting has more skill than NWP, especially when you think about model spin-up issues and things like that. So the Met Office over the last few years has been developing a suite of nowcasting tools, of which I'm going to talk to you about a few here. The first one is about making more of the data of which we have available to us. So the Met Office has a lot of observations which are coming from official sites, but obviously now, hopefully a lot of us here in the room have their own personal weather station in their back garden, I'm hoping, and we are starting to make a bit more use of that as well, feeding all of that information through and then being able to compare how the observations from everyone are really compared to the model information. So on the left-hand side here, we've got a plot of the temperature analysis. And then on the right here, we're looking at a difference between what's being observed compared to what the model, from where we thought we should be in the model environment. And we're doing this for all sorts of parameters, from air temperature to dew point. My favourite, obviously, being convergence at the surface, because when you get that low-level convergence, you're getting the ascent, and you're then getting the convection forming. And this is a great example of that. We've got a meso-analysis of our convergence fields, where our pink is where we have that low-level surface convergence. So we knew across the southwest on this day that we're expecting to see some convection, but quite where across the southwest, not too sure. It's going to be the north coast or the south coast. And using this meso-analysis, we can see with it just gives us about that 30 to 60 minutes heads up about where our risk zones are more likely to be. And we can see that the surface convection a little bit later is starting to fire in that area. So it's a really useful tool to have. The next thing I wanted to briefly talk to you about is the rapidly developing thunderstorm tool. This was made through EUMETSAT, I think with Meteo France, but obviously we're using it here in the Met Office. This is an example from about 6 weeks ago. And what it does is, from the infrared satellite, it's telling us where we have our cells which are growing, where our cells are decaying, and when our new daughter cells are forming. It's really good because it has a bold line around anything which is rapidly cooling, and that draws the eye into that area. And then it just gives us that first little hint of actually our next daughter cell is starting to form, and that's where we might be expecting our next shower to start tracking. It also has the previous track of a cell, which is the green line, and the next hour forecast if a cell was to continue on that track. Finally, it allows us to access loads of other information from the satellite data about the cloud top temperature, whether it's electrically active, and whether it's growing and what speed it's moving, etc. So that's another really useful tool of which we use when the convection is just starting to fire. The final thing that I wanted to talk to you about here in my last 5 minutes is what we then go and use in the last stage of forecasting. And this one's the most complicated, unfortunately. It's radar, apart from we're starting to look at radar in 3 dimensions. So this is our typical 2-dimensional plot of our radar. But then on the left-hand side and on the top here, we have further details about what the cloud structure is doing through vertical. So at the bottom here is low level, and at the top here is high up at the cloud top. And it's looking across this line here about what the cloud structure is across all the grid points on that line. I've got a good example in a second, which will make it a little bit easier to see. But what it's doing is it's taking multiple radar scans from all the radars and bringing all that information together. So if you've got a cloud, maybe at this point 0 here, or just the rest of it, then we're seeing, we're gathering information about that cloud from all the different radar profiles, all the different radar scans as we're moving up the cloud. And we're using that information to gather more information about the cell. Where there is information missing, then we fill that in with some post-processing and use some NWP to help us on the way there as well. So from that, we can, because we're working with dual polarized radar, we can work out all sorts of things about the clouds. We can work out about the amount of ice which is in the cloud, where that ice is in the cloud, how much liquid is within the cloud, and all sorts of things which help us work out where this cloud is in its life cycle, and whether, how much of a threat it presents in the future. And because the radars take 5 minutes to do a full scan, then then we have a scan every 5 minutes. So here's an example of a cloud, which is here at the point of which we're taking the radar, and you can see that a lot of the radar returns are coming from a fairly low level at this point, with more moderate returns at higher levels, and this is expected to track northwards into these grey squares, and the circles estimate a zone of uncertainty from a Kalman filter, which is projecting it to go northwards. And there's a load of graphs of which we can gather from here, and there's just two examples that I wanted to show you. One of them is the max return from the cloud, and you can see that it's fairly consistent when it starts to die off. And then the other one, which I've got, is the maximum top of the 45 dBz return. So this is essentially telling us the height of which hail is getting to in the cloud. And you can see that it's always up about 4,000 to 4,500 meters until the last time step. And then you can see that actually that hail isn't isn't projecting as high up into the cloud, and that's really, for me, this was only this was when we had that last big yellow warning back a couple of weeks ago. It was for me telling me that actually this little cell was going to start dying soon. So this is the cell which we're looking at here, and just to get your eye in, it's going to track northwards. This is a traditional radar. I just got to go back to the last slide. So this was at probably about 1425 to 1430. So at 1400, it's here and it's tracking northwards. And at 1425 was the last frame. And then after that, we can see that it does vaguely start to die as we move on through those last two time steps. And that helps us because I was really concerned about this little cell because it was going to go over an event or over a location which had already seen a lot of rain. And I was considering about whether to put out a piece of rapid flood guidance, of which Adrian's going to talk to you in about 5 minutes. But because that cell was forecast to die, actually, I didn't, and I held off. So what have I spoken to you about? I've spoken to you about the warnings and the guidance that the Met Office and the Flood Forecasting Centre put out. We've looked at how we start to look at some of the pre-event forecasting, and then how we use some of the tools mid-event. With that, I'm going to say thank you very much, and any questions?
So roving mic, so we'll just switch the mic arrives.
Thank you for your presentation. I've just got just a question on clarification. You mentioned soil moisture conditions. So how is that incorporated in the models?
Yeah, so that's within the grid-to-grid model, which is right at the start of the forecasting process within the surface water hazard impact model. That's where we're taking in those conditions, and that's updating every time step in the model environment, and then we run grid to grid every 6 hours to have a reanalysis. But obviously, up until then, it forecasts forward about what the soil conditions will be in the model in the model world. So that's assuming that the model is correct in its forecasting of where the showers are going to be.
Hi, yeah, thanks. I was just thinking this pre-event flood forecasting. So there's a surface water hazard impact model, but is there any pre-event forecasting activity on the fluvial side of flash flooding rather than the surface water?
No, not really beyond what happens from the main Environment Agency and Natural Resources Wales normal PDMs, which they run, which is on the main rivers. So there's that aspect of it, but assessing like the smaller non-modelled ordinary watercourses, no, not really. It's just kind of built into what we're seeing here. Well, at least I don't think so. That's my knowledge of it anyway.
Yeah, thank you for the great talk, Steve. I think for the fresh flooding, that's caused by this kind of, I think very localized rainfall. So I think as the example you show at the beginning, for the Cornwall side, so that dynamic could be really localized, I think, and change quite rapidly. I think spatially and also temporally. So I think for the platform you're talking about, so I think obviously it would be highly challenged to forecast the weather side and also the flooding side. So I think in terms of the flooding side, now the resolution is about 1 km. Yeah, so I think that's probably may not be enough, to capture this kind of localized, effect. So I think in your aspect, in your opinion, so what is the uncertainty, the major uncertainty coming from? Is it from the weather side or the flood impact side?
It's from the weather side, absolutely, and that's the limit of the hazard impact model. Is that if you're putting rubbish meteorology into it, then it's not going to give you good guidance. So that's about having a sufficiently large ensemble. At the moment, we're only really running a 12-member ensemble on it, which is pretty slack. But in the future, we are going to be running a much larger number of ensembles on it. And for me, I see that actually this will really come to fruition when we start running a really large number of ensembles on it.
How about the radar aspect you mentioned about with that, the nowcasting? Would that give more certain, I think, a prediction of the weather, I think from that?
So this summer, for the first time, we have started to run this, not from, well, so this model runs from 0 out to T+56, so 2.5 days into the future. But we have started to run a nowcast version of this, just looking at the 0 to 6 hour period of it. I've only used it once in anger on shift. And what can I say about it? What can I say about it? It's an emerging science, yeah. As with all probability on ensemble forecasting, it can say that there's a high probability of something happening, which is a 60-70% chances of it happening. If it doesn't happen, it's not wrong. It's just that it didn't happen. All the ducks didn't quite come into line. In contrast with that, if you have 2 or 3 members saying that it's going to happen and something happens, then it was a low probability and it happened, and great, it still got it right. So it is hard. And then obviously when you're running, when you've got your 12-member ensemble there, it does pick up a lot of where that risk is. So it's I think it's good in the short to medium range period. I'm yet to be convinced about the nowcast period, but we'll see how it goes and see how next summer goes.
Thank you.
Thanks. Just a quick question, kind of following up on that, and it might be a stupid one, but what exactly do you mean by the ensemble? Is that you're taking different projected rainfalls from 12 different regional climate models or local climate models and applying them to the model to work out the outcomes and then selecting the most likely, or?
So we run the Met Office's high resolution model, runs at a 2.2 kilometer resolution, and the system is processing all of those so that they're all equally likely. So we run the same model 12 times at that 2.2 kilometer resolution that's feeding through. We don't have the ability within this system to go and interrogate what's exactly going on, but with each of those ensemble members, but we can do through other things when further out. Yeah, if that answers your question.
And that gives you projected rainfall at what time step?
So that runs out, so those ensemble members forecast out to, so those 12 members go out to T+120, so 5 days in advance, and it gives outputs every hour, all the way out to 5 days.
Just sorry, so it's one model and you run it 12 times basically with the same input parameters, but it just comes out with different results each time.
Yeah, slight perturbations within it through to change in the you add some slight perturbations through the system, and actually especially when you're looking 4 or 5 days out, the input from the lateral boundary conditions comes from the global ensemble. So therefore, if there's some fluctuation, some uncertainty within forecasting some convection in the eastern USA, and that might be affecting the how sharp a trough is, let's say, because of what time that convection fires. Maybe if it fires a couple of hours earlier or a couple of hours later, it's going to change the upper pattern, and then that feeds all the way downstream into the ensembles across the UK. So it's about picking up all of those uncertainties, even across the other side of the world, really.
Thanks.
Okay. Any final questions, Stephen? Excellent. Thank you very much for your talk then. Thanks everyone for the questions. Didn't take us very long to get to the grips of this problem that we have uncertainty from the weather, uncertainty in our flood models, and we're dealing with low probability forecasts. So hopefully they're themes that we're going to explore more through the rest of the session. So now I'd like to invite Adrian Wing from the Flood Forecasting Centre to come up, and it sounds like you've got a good double act and you can now follow on from what Stephen's been telling us. Thanks, Adrian. Thanks,
Linda. We certainly have got to the nub of the problem quite quickly. Yeah, thanks for inviting me here. I'm Adrian Wynne. I work for the Flood Forecasting Centre in Exeter with Steve. I'm a chartered meteorologist. I'm also a member of the BHS, have been for more than 20 years, I think. And I'm going to tell you what I've been up to for the last 2 years. So a quick rundown here. I'm going to look at a bit of background to our surface water service, although Steve's already covered some of that. Some of the challenges in surface water forecasting, which again, we've already touched on. A bit about the project that I've been working on leading up to the Rapid Flood Guidance Service. And then if I've got time, I'll run through a case study on that as well. So background to our current surface water forecasting service. So since 2009, the Flood Forecasting Centre, so joint project between the Met Office and the Environment Agency, I've been producing this flood guidance statement, which Steve talked about. And that's covering 4 sources of natural flooding, so fluvial, surface water, groundwater, and coastal. So that has been, for the last 15 years or so, basically the offering for surface water flood risk awareness. So it's worth just dwelling briefly on what's in that and why we need to move on from that. So we're using this sort of probabilistic approach here. So we're looking at the likelihood and the impact of surface water flooding. But what we're drawing is really quite large polygons across England and Wales. So if you think back to the hazard impact model that Steve was showing, we zoomed right in to a tiny bit of a map there, and then we've zoomed right out again to give our awareness, our kind of risk information to our partners. This product goes to category 1 and 2 responders. So it's for professionals responding to flood incidents. So we give these broad scale polygons, and we issue this product once a day. It comes out at about 10:30 in the morning. If the risk is significantly elevated, we'll issue it again in the afternoon. But generally speaking, it comes out once a day. And the forecast information that goes into it is more or less a sort of daily process. And then alongside these sort of pictures, we give this little scenario. You probably can't read that, but basically it's giving some quite broad scale information about the surface water flood risk. It's not mentioning any locations. It talks about parts of South Wales, South England and the Midlands, and that's as specific as it gets. And also note that down the bottom here, it says impacts could include localised flooding from urban and fast responding smaller water courses and drains, channels and flooding from overland flow. Just moving into that intersection between sort of true surface water, which is, drainage problems, into the sort of smaller fluvial elements, which is the fast responding small rivers, which might or might not be main rivers by the Environment Agency's definition. So that's what we're doing at the moment. So the question is, why is that such a broad scale forecast? Why can't we do something more specific? And I don't mean to be too slopey shouldered about this, but it's because it's really hard to do, and Steve's touched on some of this already. So with river forecasting, I'm not saying that river forecasting is not hard, by the way, but with river forecasting, it can be quite predictable. There are parts of river forecasting where you can say, actually, we can wait until after the rains hit the ground before producing this forecast. We can route the flow down through the river systems to give warnings about known places sitting by rivers that we know flood at particular times, and we know how that flood peak moves down. With surface water flooding, we can forecast the broad scale ingredients with the same accuracy as that. But it's when we start to try and zoom in a little bit that we start to have problems. So as we move into more like county scale forecasting for surface water, we can do that from a rainfall perspective, but we have to use a probabilistic approach. And that works and it gives helpful guidance. But as soon as we start to overlay the probability of a rainfall amount on the probability of an impact, that's when we really start to have problems. Because we might be able to say there's a 30% chance of 60:1 rainfall, and we might observe that, but the number of times that 60 millimeters in 1 hour will actually produce a significant impact is much smaller. And if you think back to the map that Steve showed, that rain's only got to move by a few hundred meters to go from significant impact to no impact at all. So we've tended to stick with the broad scale. So I'm going to step back from that a minute and look at our surface water improvement project and the problem that was trying to address. Firstly, the NAFRA2 data came out, National Assessment of Flood Risk, basically told us that a huge number more properties were at risk from surface water flooding than we had previously thought. There's some statistics up there. So about 4.6 million properties, 43% increase on our previous assessment, which was done in 2018, and 1.1 million at high risk. And that's not something that the government can sit back and ignore. So on our national risk register, surface water has increased to a significant risk. So that's on a par now with the risk of river and coastal flooding. So that's one of the highest environmental risks faced across England. So that's where the project that I've been involved with came about. And the brief was to firstly understand and improve our capability, and that's broadly what Steve's been talking about so far. And secondly, to improve the responder community's understanding with some improvements to national flood guidance. So with that piece of information, with that sort of brief, we set about trying to improve our surface water hazard impact model, and we went straight to our responder community and tried to research their needs. So we've got this new information about surface water flood risk. What do our responders, those Cat 1 and 2 responders, say that they actually need practically to improve their service? And what they told us was, firstly, don't throw the baby out with the bathwater. So the FGS is a good service. It's very much relied upon by people. There's no appetite for fundamentally changing that. Secondly, it was that 0 to 6 hour lead time that they wanted more information on. So as I said, the flood guidance statement is issued once a day at roughly 10 o'clock. By early afternoon, that information could well be way out of date. And they wanted more frequent updates on that. And the sort of updates that they wanted were simply where and when. So with all that in mind, I was briefed with developing and running a trial service. So that's what I tried to do. So the first thing that I looked at was this kind of, this business of why can't we just give more accurate surface water forecasts? Well, we know that's not really possible at the moment. We're working on it. But what information could we share? What information do we have? As we're sitting there after we've issued our flood guidance statement, what sort of information do we have that we could possibly be sharing with our partners that might make their lives better? So firstly, we're constantly monitoring the weather when we're on shift. We're looking at the development of those convective systems. We're looking at observations from radar, from rain gauges. So we have quite a good idea of how the weather is developing. So why weren't we sharing that with our partners? And secondly, we've got those new tools that Steve's been talking about. So the cell tracking, mesoanalysis, and the radar tools. To be fair, those are very much in their infancy. We're still learning how to use them. Not all forecasters have access to them, and not all forecasters are confident in using them. But we could start to bring that in, and where we do have that information, surely we should be sharing it. So the next thing I did was to go back to the users and say, well, here's the information that we've got. Could we give it to you on some kind of short notice basis? And if we did, would it be useful? So we got together about, I think, 140 of our users, and we made a sort of panel, and we went backwards and forwards with them saying, we could try this, we could give you this information, and they told us what they thought. So for quite a few months, we went round and round that circle, and that was a really important part of this piece of work, was that it had to be user focused, because there's no good just throwing information at responders without knowing that it's going to be of some use to them. So we looked at things like, the hurricane type, cones of uncertainty. We looked at sending them radar data, rain gauge data, and we gradually refined it down to what we thought could work. And that's what became the trial service for rapid flood guidance, which we ran in 2024. So that was a 24/7 live trial. So 1,700 responders signed up for that. And over the summer of 2024, we issued 55 rapid flood guidance updates. And we kept in touch with the users throughout that process. So they were asked to feedback whenever they got a rapid flood guidance. And then for specific events, we carried out studies on those events, and we sort of proactively went out to the responders and said, you received this, what did you do with it? What decisions did it help you with? what were you able to do that you might not have otherwise been able to do? And broadly speaking, people very much welcomed it. So 84% of people said that they had a positive experience with the trial. And there's a fairly overwhelming reaction that people thought that that service should continue. And so that developed into the Rapid Flood Guidance Service for 2025, which is currently running and will end on the 17th of this month. So I'll tell you a little bit more about the Rapid Flood Guidance then. Essentially what it does is it gives updates to the flood guidance statement. So it's designed for flood guidance statement users, and it gives updates when flooding could develop rapidly, or which we call less than 3 hours. So the first thing we do is to mark up the flood guidance statement itself to indicate that we're emphasising the flood. That's the wrong button. That's the right button. So with this little badge here, we indicate on the flood guidance statement that we're emphasising the surface water risk on that day and that we might issue rapid flood guidance. And then on the day itself, we issue these updates. Sometimes they come with zero notice at all. So occasionally we're able to give some lead time, but sometimes there's actually no lead time at all. But what people have told us is that's still useful. So even though they're in the middle of an event, the fact that we're contacting them and saying, we know that this is happening, this is where it is, this is where it's moving, it's likely to last this long. They're still telling us that's useful information. And I think that's possibly where the step forward has come, that I think previously possibly we were saying, well, if we want to forecast surface water impact, we need to be able to give a certain amount of lead time. And actually responders are telling us that that's not necessarily the case. So it's one product, it's just a PDF document. I've done it again, button. So it's one PDF document which we update through the day, and it gives a national summary. That's broadly aimed for national type responders, so people like DEFRA, Environment Agency managers, who need to see the zoomed out picture. And then for specific areas of concern, we give these polygons, and we give an idea of the what's happening now, what's going to happen in the short-term future, and what sort of areas are likely to be affected. We deliver it through the current flood guidance statement route, so we send people emails, and they can get an SMS service. They can sign up for it on Hazard Manager, and they can sign up on a county basis now. So that means they're not getting loads and loads of alerts for stuff that's at the other end of the country. They can sign up for their specific county or counties. And it's a seasonal service, so it runs from May through to October. An important part of this is the way that we produce it. So we're working very closely with the Expert Weather Hub in the Met Office. So the Expert Weather Hub is the team that consists of the chief forecaster and the deputy chief, and some other roles. And they produce, if you like, the raw material for the rapid flood guidance. So they produce, using the techniques that Steve's talked about, they produce these nowcasting updates. And they're forecasting for forecasters effectively. So they're giving guidance to other forecasters within the Met Office. So this guidance that they issue here is it's written in a kind of meteorology speak, and it's broad, and it's disseminated internally through the Met Office. And what we're doing is picking up these pieces of information. So we've got a polygon here, and we've got some text, and it's got some rainfall amounts in it. We've built a system that can pick up the polygon and automatically put it into our RFG production system. And then the Flood Forecasting Centre then decides what the impacts are likely to be as a result of that. And so the Flood Forecasting Centre make the decision to issue and add the context and convert it into the customer format. And we try and do that in 10 minutes from the point where we receive that polygon in our system. We try to get the rapid flood guidance out in 10 minutes. Sometimes we do, and sometimes we don't. So rapid flooding is any flooding that starts within 3 hours of rain. So it's not, strictly speaking, surface water flooding. It could be any type of flooding. And just to note that it's not altering any of the existing responsibilities between organisations. So we're sort of overlaying this as helpful information rather than stuff that produces new procedures. I'm going to quickly go through a case study just to try and give a little bit of context and explain a bit more about how we deliver the service. So here's an example from the 31st of July this year. So we've got a fairly complex series of fronts surrounding the UK, and you'll see that we've got a cold front across southern UK, and that's going to provide the focus for shower development. We've got a few factors that are limiting convection. So we've got limited shear, and we've got 15 to 20 knots of steering flow. So the limited shear means that the cells are probably not going to grow huge and organised. The 20 knots of steering flow is going to mean that stuff gets moved on quite quickly and doesn't really affect any one location for too long. But on the other hand, we've got flow parallel to a sea breeze convergence line, and that could mean that repeated cells develop in one area. There's some rainfall values that we settled upon, and so that's what our flood guidance statement looked like. Again, broad area yellow, and rapid flood guidance badge. And that's the UKV forecast, so the short range 1.5 kilometre forecast. The forecaster would have been seen at about midday on that day. So by 2 o'clock in the afternoon, we were starting to see the showers developing, and the forecaster issued this rapid flood guidance polygon here. So basically saying we're seeing these showers develop. This is where we could be seeing some more rainfall. And that was updated a couple of hours later. So at 4 o'clock, we've seen that that's been quite a persistent line of rain there. So we've narrowed that down a little bit, and we've included the north of the Isle of Wight in there too. A little bit later on, we're seeing that these showers up in Gloucestershire becoming quite persistent. So we issue another one. So that's polygon 2. So our rapid flood guidance has now got the updated polygon 1, and it's got polygon 2 on it as well. This one is giving some indication of the shower movement, and again giving some idea of the rainfall amounts. Back to polygon 1, so a third update for polygon 1, because this line has now moved south and it's intensified and it's affecting the north side of the Isle of Wight. So this polygon's shrunk quite a lot, and we're now talking about even more rainfall. And then finally, at 8:30 in the evening, we issue a final update to tell people that we can now see that this is basically moving offshore and decaying. So responders told us that they were keen to have a final update, which effectively closes off the event for them. And that's what happened in reality. So we flagged that up as minor flood impacts, really because of the numbers of properties that were affected. So quite dramatic for some of the people that were, living in that area, but from a responder point of view, probably an ordinary day's work. And worth noting as well, there were some minor impacts in Lincolnshire, which we didn't mention in our rapid flood guidance, so it's not perfect yet. And I'll stop there and hand back to Linda.
Thank you, Adrian. So now we've added another challenge, kind of meeting our uncertainty and linking it through to what people actually want and how we can support decision makers. So adding the pieces of this puzzle together. Open to any questions from anyone?
Thanks for the presentation. Just a question, I think you mentioned a timeline that it runs from May to October, and then just wondering about that timeline with some of the more significant storms in kind of Yorkshire being kind of winter and early spring.
No, that's a really good question. So we've got summertime convection is perhaps an easier problem to resolve in terms of the link between rainfall and impacts. As we move into the winter, we start to see impacts at short notice that could that are affected by other aspects of weather and hydrology and infrastructure. So, for example, you might start to see flood defences being under stress, and there might be a risk of a flood defence failing. Do you then issue rapid flood guidance to cover that? And then you end up in that sort of complex responsibility area. So really it's the Environment Agency's job to issue warnings for those sorts of effects. So it's a little bit of a cop-out in that we're staying in the space where we can clearly see the link between rainfall and impacts. Some people have said it needs to be a year-round service. At the moment, we're resisting that because there's all that complexity with the flood warning service and the possibility that rapid flooding could be caused by lots of other complications.
Hi, thank you for that. How much more effort is doing the service throughout the day rather than just once daily? How much more effort do you have to put in?
It's quite a lot of effort actually, and one of the things that we've discovered in the trial was that our operational hydromet, so the hydrometeorologists who produce all the guidance, found that just that sort of awareness role of being constantly aware of the possibility that they might need to issue rapid flood guidance meant that they were under quite a lot more stress during the day, even if they didn't issue anything. So the actual issue process, we hope, as I say, it's about 10 minutes work, but the monitoring and the thought process that goes into that, it makes it much more complicated. So what we did this year is that we've actually had a role that runs from 9 o'clock in the morning to 9 o'clock in the evening, specifically to issue rapid flood guidance. So of course, those people most of the time have done nothing. I think we've issued about 12 or so rapid flood guidance updates this season so far. So most of the time, those people are doing nothing, but it means that the hydrometeorologists doing the rest of the job can focus on what they need to do. So there's that overhead. So it's quite expensive in a way to make sure that you've got the people in place to do it.
Thanks. Just following on from that, so how much of it is automated and how much of it are people actually doing?
Very little is automated at the moment. So the only real bit that's automated is the transfer of that polygon that's been drawn by the Expert Weather Hub. So that is sent automatically into our production system, so we don't have to draw the polygon, but we do have to, and the guidance that comes with that, so the text is also pulled into our system, but we've still then got to position that on a map, write the guidance, and I suppose the big bit is the thinking process about who do I want to warn when, what's the right moment, are we really going to cross that threshold? So it's that thinking process. So there's quite a challenge coming back to us from the Met Office to say we need to automate this as far as possible. I think we're a little way from being able to do that at the moment, but it's something that's very much on our minds. So yeah, good question.
Hi there. Thanks for the talk. I'm just wondering, as a user of a consumer of the rapid flood guidance, and what would be most useful longer term, pie in the sky type thinking. Is there an ambition in the future to kind of go to the next step of actually issuing flood mapping associated with the warnings and areas of inundation, or is that just too convoluted, too complicated, too uncertain to be useful?
I think that's certainly the direction of travel. And one thing I meant to say actually was that we don't see rapid flood guidance as the solution to the problem. It's very much a kind of stopping point on the way. So it's the first step, and it's very much a kind of stopgap service really. So absolutely we need to improve our capability, and ideally we need to get to the point where we can share much more specific real-time information. The question at the moment is how that works into the different responsibilities of the different authorities that are involved. So you've got the Environment Agency involved, you've got lead local flood authorities involved, then you've got the Met Office, UK Weather Warning Service. So we need to make sure that any work that takes place in that area doesn't muddy the waters too much, and that there's a sort of clear line of responsibility as to who should be producing that guidance. And I think very much the Environment Agency need to be involved from that flood mapping point of view and identifying local communities that need to be told about it. So it might be that would be seen more as an extension to the Flood Warning Service than an extension to the Flood Guidance Statement Service.
Makes sense. Thank you.
Hi, yeah, Anita Asajula from Environment Agency and Flood Hydrology. It was nice to see in the rapid flood guidance statements that it's watercourses as well as surface water. Sorry to go on about this. I'm from the hydrology side. But I wonder I saw on some of those examples, it sort of said, you know, flooding likely in like low-lying rural areas or surface water flooding. But there was one that said, you know, and flooding likely in watercourses. So are you using like catchment information or like how steep the catchments are, or to know when to say, watch out for your watercourses? Or how are you deciding when to?
Yeah, so we're very much trying to incorporate, you know, the risk from rapid response catchments is very real. We don't have great capability in that area at the moment. So what we have is the input of monitoring and forecasting duty officers from the Environment Agency. So they're running all the local models. So any local modelling capability that we have, we hope would be already processed as part of the flood guidance statement. So they tell us there's a risk to small rapid catchments in this period, in this area. We then incorporate that into the flood guidance statement. And when we come to issue the rapid flood guidance, what we're trying to do at the moment is to look at the polygon that's been drawn by the Expert Weather Hub and say, well, actually that polygon needs to shunt into this urban area or into this area where we know there are rapid response catchments. So our capability at the moment is simply looking at a shapefile of rapid response catchments and using that to influence where that polygon goes. But we'd very much like to expand that capability a little bit to be probably more rapidly updating so that we can see when there's a genuine response forecast from a rapid response catchment.
Thank you.
Okay. Oh, one last question then here.
Just a quick one. What's your threshold for issuing the warning? So yeah.
Good question. I've been challenged a lot on this. My personal threshold is whenever information would be useful to the responder community. But Hydromets don't like that at all. So the threshold, broadly speaking, is aligned with column 3 in our flood guidance statement. So that's significant impacts. So it's quite high. When we did the trial, we had more minor impacts. So column 2 in our matrix. And what we found was that along with the fact that we only had regional sign up meant that loads of people got a whole load of guidance that wasn't relevant to them, or they were getting loads of guidance but nothing was happening. So for this year we upped it to roughly significant, but I'm quite keen that we emphasize when we're verifying it that it's about how useful the guidance was rather than, you know, technically we observed significant impacts. So the example I showed was we issued rapid flood guidance, but we only observed minor impacts, but we didn't get any feedback saying you shouldn't have issued that. And I think most responders were probably pretty happy with it.
Thanks very much, Adrian. Okay, so we're moving on to the last presentation in this session from Fatima Pilosu from ECMWF and the University of Reading. So we're going to broaden out from the Met Office and the Flood Forecasting Centre and hear about some international development. hand over to you, Fatima.
Good morning. My name is Fatima Pilosu. I'm a PhD candidate at the University of Reading and a visiting scientist at ECNWF. We are going to talk about something completely different to what we have seen so far. I'm going to basically talk about prediction of flash floods at medium range and at the global scales. So if we want to move toward early warnings for all, and I'm not just talking about the UN initiative, but the underlying principle that everyone should be protected by some kind of forecast with actionable predictions. We need accurate predictions, of course, to reduce false alarms and missed events, to basically maintain high detection rates, especially when resources are limited. We can think, for example, at forecast-based financing in this case. We need actionable lead times. In certain locations, it's not enough giving them guidance just a few hours before, especially, let's say, if you need to warn remote communities. And then, of course, we need to have continuous global coverage to produce seamless forecasts. To achieve this, we need, of course, input data, the observations that can be stream flow, impact data. We need very accurate rainfall forecasts. We go nowhere without them. And then we can start, after that, we can start thinking about adding other parameters that are very important, like soil moisture and catchment characteristics. Of course, we need a model, you can have a fully distributed hydrological model, but at these scales and at these lead times, it's extremely difficult. So we decided to use AI-based models. Then we need to define our warning thresholds to basically give some information about what kind of magnitude, how severe these flash floods might be. And of course, we need to run offline verification. This is really, I don't know, I don't want to exaggerate, but 60–70% of my time, because when we talk about flash floods, they can be also so political because of their responsibility and the damages. We're talking about people dying by these events, that we need to really provide solid verification about how these forecasts perform at day 3, day 5, and so on. So my presentation is going to be organized in these 4 parts. The first one, I'm going to talk about how we have improved rainfall predictions from global models. What do we know from those is that if we compare the distribution of rainfall forecasts from global models, they underpredict the frequency of small totals. We know we overestimate small rainfall values, and we underestimate we underestimate these extreme values that basically are fundamental to issue flash flood warnings. So what we want to do is basically map the distribution, the rainfall forecast that we obtain from global models into the distribution of localized rain gauge observations. How do we do this? So we have seen in the previous presentations, you can use nowcasting, you can use high resolution models, but they have always some issues if you want to produce forecasts at global scale and medium range. They produce very good distribution of rainfall totals. The location of extreme is very good for nowcasting. Sometimes they are mislocated in high resolution NWP models. The problems arise when we start talking about lead times. We are talking about just mere hours or maximum up to few days. So we cannot go really into these medium range scales. And the spatial coverage is what it is very limited. I want to acknowledge now, for example, at ECNWF, we have Destination Earth running on a daily basis at 4.4 kilometers, but it is still a deterministic model. So when you want to predict something at medium range, the random errors that you're going to have from these kind of observations, they make it borderline useless at day 5 and beyond. So we want to use the information that is contained in global NWP models. Lead times are very good. We can use potentially even up to day 15, and the spatial coverage is already global, so it's what we need. But we still need some work. We need to do some work on the distribution of the rainfall totals and the location of the extremes. And what we can do is post-process these models. But as we know, with traditional post-processing, it's extremely difficult to create something that it can be applied everywhere. So this is the, oh, blimey, what happened? I pressed the wrong button. Okay, fine. It's the white one, okay. This is the name of the post-processing technique that I collaborated to develop at ECNWF. And the underlying concept for this is the remote calibration. So let's assume you want to post-process rainfall forecasts. We took here Louisiana, over mainly convection, light wind conditions in summer and in a flat area. Typically, what you would do is sit in Louisiana, wait for 20 years, and hopefully you will see these conditions often enough to post-process your global model for Louisiana in these conditions. But what if we can have observations for similar conditions elsewhere, and we can use those to post-process the forecast for Louisiana? The details of the methodology, you can find them in the main paper, but the benefits here are we create a huge training data set. We are talking about millions of data points compared to just few thousand if you are lucky. We have global point scale rainfall predictions everywhere, even in locations that have 0 observations. And we have no non-stationary issues because we don't have to wait for 20 years and use data from a climate that is not representative of today's climate, because if we can use only 1 year of global data, so we represent today's climate. So basically what you obtain is this distribution that we call mapping function. And basically what it is just a distribution of the errors between that you have when you compare your forecast with the observations. And this distribution is, I subdivided it in 3 areas. The green area is where the model overestimates, especially the small values or zeros in this first bar. We have the area white, where the model is representing fairly well the point observations. That's why it's white. And then we have this yellow and red area where the model underestimates, which is the most dangerous situation to have, because that's when you miss the flash flood events. So this distribution, you can use it to, from your one single forecast, create a distribution of values. And what you will say is, if your model gives you, I don't know, 10 millimeters of rainfall, then you would say that 20% of the time you might have actually 10 millimeters, but actually you can have quite a few zeros, and then some small probability of having, I don't know, 50 millimeters, which if that is your trigger for flash floods, your probability now is going to be not 0. We can use that distribution of the errors to post-process our forecast, but that's not actually what you want to do, because then you will be post-processing all the grid points in the same way. What you want to have is a decision tree where you split your errors using different weather conditions, which we call weather types. And you can see that these you can have very, very different distributions. In case A, you have a distribution that is telling you, actually, your model is giving you forecasts that are representative of point observations, while case B, which is a typical condition of convective rainfall, you might have quite a few zeros, but you still have quite a small, decent probabilities of having much bigger rainfall totals. I'm not going to go into the detail of the verification. If you are interested, you can refer back to all these papers where we verified easy point against global ensemble, raw ensemble, but also against kilometer scale models. And we show that actually easy point outperforms both of them against point verification. I just focus on reliability because one of the main questions that I'm asked is how reliable is your prediction? And we can see that when we use the multiple weather type post-processing, we are extremely reliable for extreme rainfall. Sorry, I didn't add that. This is for a rainfall event exceeding 50 millimeters in 12 hours. So whatever the probabilities we give, they are extremely reliable. And here I'm just showing one example of how the rainfall products look like. This is for the flash floods in China. You can see here, these are the observations, and we have very localized extreme 465 millimeters in 12 hours, and all around them, very, very little rainfall totals, almost zeros. And this is a typical condition that is extremely difficult to predict. The ensemble up to day 5 already gives some decent indication where the areas of high rainfall might be, but you can see that they are underestimating them quite, at least they are just producing only half of the rainfall totals that were actually observed. When we post-process with one single weather type, we are overshooting the prediction, showing that it's not a very good idea using just one single weather mapping function. But instead, when we use the decision tree, it's not showing this here, we have a much better representation of the actual extremes that we might have. And not only for the extremes, but also for the zeros. The probabilities of having a zero rainfall total are almost 90%, are around 90% for the multiple weather type easy point compared to the others, where also the ensemble says it's a 0. So we can give that information that is extremely useful at medium range of conditions where you might see nothing happening in your area, but if something happens, might be very extreme. So now I go on to how we define the thresholds to understand how severe an event might be. So this was created in a project that I was not involved personally. This was the Highlander project together with Cineca in Italy. They post-processed ERA5 rainfall and temperature. I'm going to focus on the temperature, on the rainfall. But if you're interested, there are these 2 publications where we show verification for both of the parameters. We have created from this project 24-hourly and 12-hourly historical data from 1950, and now we create also near real-time data. In the verification that I conducted globally, we can see again that the ERA5 easy point produces it produces much better distribution of point scale rainfall. Is extremely similar. Why do I not see? Fine. You can see in the orange circles that you can that easy point represents much better the zeros and the whole distribution of point rainfall totals compared to any other model climatology that are typically used. And this is done in flat areas and in mountainous complex orography. And this is, again, how this rainfall data looks like. This is for the Valencia floods last year. If we want to analyze this event just using ERA5, which is what typically people would do, we will see that if this event is not very well represented. We have up to anything between 80 and 100 millimeters in 12 hours, while we know we went up to 700. So it's a massive underestimation. ERA5 is a 31 kilometers, so we expect this underrepresentation. But if we create a distribution of point rainfall values, then we are able to give a much better representation of these localized extremes. And in this particular condition, we got up to around 600 millimeters in 12 hours. Now I'm going to talk about the development that we did during my PhD about the prediction of areas at risk of flash flood. And I cannot start talking about this problem without discussing the problem that affects us all that do AI development, which is the scarcity of data. We have seen before it's a problem at more local scales and national scales. At global scales, it's just soul destroying, basically. You can see here the flash flood reports from NDAT in 2024, and we have only 143 events. This is actually not that much, and you can see here why, because we have only few flash flood reports in few countries, but I can tell you, Italy here, it has a 0, and we did have some events. So what you can do is look at other regional events and other regional databases. And suddenly you see actually, for example, in the US, we have 5,000, more than 5,000 events in 2024. So we could potentially use this database. It's not perfect, but we can start seeing some improvements. For example, we can see the climatological distribution over the year with more events over the summer. This would be completely missing other databases. But you can still see that there are some problems, some different distributions, spatial distribution, more over the east, less over the west. This is due to the climatology, rainfall climatology, but it's not, we know that we are underestimating the frequency of flash flood events in the west. And especially as well here, all these dots represent grid points on our domain. And you can see that not many of them, most of them, they have 0 events, which basically creates a training data set that can have 20 million of data points, but only 50,000 have events. So this is what technically is called a severe imbalance data set. But it's not completely a disaster, because we can use some information to extract, some methods to extract information from this imbalanced data set. And what I always say for flash flood modeling, less is more. Less parameters is better. We know rainfall is fundamental. I discussed how we try to improve the data. We use these 2 parameters because after many combinations, this gave best results. We can use soil moisture, in this case from ERA5, and then we can use some other parameters, static, climatological, like the standard deviation of the orography, to assess how complex is the orography in a specific grid points, and the leaf area index, because we know in bare soils we are a higher risk of flash floods. And I invite you to remember what I just said, because these 2 parameters are going to give us very interesting results. So again, less model complexity is more. We are all reading every day, potentially we can read about the new, very complex AI model for river and flash flood prediction. But here I decided to go extremely simple and use models that everyone is familiar with. I just selected 3 different categories because they extract information from the data in different ways. And I will spare you with all the tests that I did during my PhD, and I just go straight to the result. XGBoost in boosting gave the best results. because of the way that treats the data. It gives more weight every time that creates a decision tree, gives more weight to misclassify predicted samples. So really tries to gain as much information as possible from that minority class that contains so extreme valuable data and information. Neural networks gave similar results, but I chose XGBoost because the training time is in the order of hours compared of days. And as I said, I run the Sharpe values to try to understand how the model got to the observations. And we see that total precipitation is the most important parameter. And then we got the leaf area index as the second most important, orography as the third, and the soil moisture. Personally, I would have given the standard deviation of the orography the most important, the second importance. But the leaf area index came as the second, and it gave very funny results. It says if you have a much bigger leaf area index, you increase your probability of flash flood, which is what is the opposite to what we would have expected. And this is because it was correlated with rainfall and with the climatology of when the flash floods happen. The standard deviation of the orography says that if we have smaller standard deviation of the orography, we increase the probabilities of flash floods. And this is related to the fact that the impacts happen in flat areas rather than complex orography. So it would be, it's the opposite to what you would expect, but perhaps if you integrate this training data set with streamflow, we might get some different results. So this shows how important it is to know your data. How the predictions look, basically we give probabilities on a grid for what is the risk of having a flash flood. And this is the Spain case. We can see that in the location of Valencia, we are giving between 5 to 7% of probability that something might happen. And this is not just this is in the reanalysis, but at day 1, at day 2, we go also higher probabilities on day 2, day 3. So it's a bit up and down, but again, it's giving very good indication where, again, it's not working, again, where the areas might be few days in advance. I'm not going into the reliability because I'm running out of time. I'm just going to say that we are able to give very reliable predictions at day 1. 10% probabilities are still reliable at day 1, and they does decrease at day 3 to more or less 5%, and then and they reduce to 1-2% at day 5. And the conclusions, just to finish, the lessons learned from these last 10 years of working on this. This is a quote that I've seen many years ago and has driven my research until now. It says, the ability to simplify means to eliminate the unnecessary so that the necessary can speak. Less parameters. You have seen, I haven't used a huge list of parameters. Few parameters that we know from the literature can really help to inform these models at global scale, medium time range. To input the predictions at a site, we should not be using observations only from that site. We have seen the successful stories of the remote calibration in Easy Point. If we want to improve the predictions at one particular site, it's best to use all the observations that you have potentially around the globe. But also, this is Google's approach now in their hydrological modeling. They use all the information from different catchments around the world to train just one model and then predict at different sites. And finally, we must get comfortable at predicting extreme rainfall and flash floods with small probability forecasts. I didn't show this now, but fundamentally, if whenever some extreme event happens, we are predicting on average this event with 1, 2, maximum 5% probability. And we should not be calling those, when something doesn't happen, we should not be calling these non-events false alarms. These are negative connotation that stop us predicting very, very extreme events that can trigger deaths if nothing is issued, no warnings are issued. Thank you very much.
Thank you, Fatima. Very interesting presentation and some good conclusions for the whole session there. We've got a couple of minutes for a couple of quick questions before we move on to lunch. Unless everyone's just focused straight on lunch. Yep, over there.
Hi, thanks. That was really interesting. I didn't quite get your conclusion around the leaf area index and how that was the best predictor of flash floods. It relates to that vegetation's there because there's a greater probability of rainfall in that location.
So basically the conclusion is the leaf area index it has its biggest during the summer. And that's as well where you have the higher frequency of flash flood events. So what I have so far understood is that because the model sees higher leaf area index where it sees the higher frequency of flash floods, it says, oh, it must be correlated. And it is correlated, that's what happens, but not necessarily causes the flash flood. Actually, we know when we have bare soils, like after a wildfire or snow, or it's just not a vegetated area, you have a higher risk of flash floods. So I think this is what is happening. So my conclusion is we should not be using leaf area index in this case. It's giving the right answer for the wrong reason.
Okay, well, in the absence of questions, I think we'll move on to lunch to keep the time. Thank you, Fatima. Please chat to Fatima at lunch if you have any other questions. And thanks to all the speakers in this session. I think it set us up with a good understanding of some of the challenges that we have with integrating the meteorology and the hydrology to do flash flood forecasting well. So we'll continue the discussion over lunch.
Okay, shall we get started? Okay. Give time to come back. Welcome, everyone. Welcome back. So this is session 2, all about climate change and changing risks. So I'm Professor Lizzie Kendon. I'm strategic head at the Met Office. I'm also leading the Future Flood Project, which you're about to hear about. So first speaker today is Laura Devitt, who's from Bristol. So she's working with me on the Future Flood Project, which is pulling through the latest high resolution climate projections, UKCP local, for those who are familiar with it, into flooding and understanding how flooding might change in the future. So she's working to produce new, evolving, spatially detailed estimates of flood hazard and exposure. So Laura, welcome. Sorry, I'm losing my voice. Okay. I'll give you 5-minute warning. Okay, thank you.
Hello, everybody. I'm Laura, as Lizzie has said, and I'm a postdoc at the University of Bristol. I'm working on the Future Flood Project, which is a project with colleagues from Bristol and from the Met Office. The project started in 2024, and we're running to about 2028, so we're about midway through the project. And the main aim of the project is to produce evolving projections of future flood risk over the UK and making use of the high resolution UKCP local projections to look at how national scale flooding will change and including pluvial, fluvial and coastal flooding. And the project is made up of several components. The first is to assess how heavy rainfall events changes in the projections over time. And then we're going to use the projections to force national scale flood models and hydrological models to look at what that rainfall does to flood risk through time. And then from this, we're hopefully going to be able to identify some practical guidance that we can share with the rest of the community. So today I'm going to just share some of our first results, focusing on how the heavy rainfall events changes in the UKCP local projections and what this might mean for future hazard and risk. Okay, so I probably don't need to tell anybody this, but flooding is projected to become much more frequent and destructive in the UK. And so far, the national risk assessments that we have done in the UK have used one of two methods, or combined. We either use coarse resolution models, so daily models with like a 15-kilometre spatial resolution, or we derive simple intensity uplifts that we can apply to both rainfall and river flows to account for changes in the climate. So applying a simple percentage change to peak river flows or rainfall intensities. And these methods are able to capture average intensity changes quite well, but they're not able to look at things like shifts in event size, timing, and how they might cluster as well. And these are all really important factors for flood risk. And so like a summer downpour will look really different to a peaky winter event. But if we apply an uplifter factor, it would treat those two events as the same. And they're physically not the same. So yeah, this is something that we're going to explore in future floods. And one of the things we want to do is say, how is rainfall going to change and what that means for flooding, rather than just by how much. Okay, so to address this, we're going to be using the UKCP local projections. This is a 12-member ensemble, actually 16-member ensemble now, with transient simulations that cover a 100-year time period and run at an hourly time step with a grid resolution of 2.2 kilometres, but we've been using the 5-kilometre version. And in these projections, convection is explicitly represented. And this is really important because it's able to capture short, intense bursts of high intensity rainfall, things that are really important for flash flooding. And so this gives us a really exciting opportunity to look at how extremes change through time, and we can drive national scale flood models with these to see how that directly impacts flooding. And so instead of just calculating change factors and applying those to rainfall fields or river flows, we can look at a complete distribution of plausible rainfall events, and we can see what that does to the different types of flooding that we get, so pluvial, fluvial and coastal. So the project has 4 main components. So the first one is to get an understanding of what is happening inside the rainfall projections themselves, and get a bit of an understanding of how the characteristics of heavy rainfall are going to change. And then we're going to use that rainfall to force national scale flood models. So forcing a hydrological model, which will provide the peak flow events that can be used to force the fluvial flood model. We're going to be using the rainfall itself to drive the surface water flood model, and we're going to be including some coastal boundary conditions as well to account for compound flooding at the coast. And then once we have all of those hazard maps, we want to really dig more into the results themselves and try and get a real understanding of the processes that are driving the changes in flooding. So trying to identify what it is about the rainfall changes that we're seeing that then changes the way we experience flooding. And then from this, we're going to be creating some impact demonstrators and some guidance. So we already have a national scale demonstrator in production with the Department for Education, looking at how surface water flooding is impacting schools across the UK. And we've also got some more local scale impact demonstrators with local councils and authorities. But in this talk today, I'm going to be talking about the results we found so far in the national scale analysis of the heavy rainfall events and some initial results from our pluvial flood risk modelling that we've been doing so far. Okay, so to capture changes to rainfall events, we've taken an event-based approach rather than just taking a statistical, using a statistical methods on AMAX series or something, something like that. So I will just quickly give a brief. It was quite a complicated, well, not complicated, it's got many steps to the method. So I'll just briefly go over. So we take the UK and we split it into 12 sub-regions that roughly correspond with the hydroclimatic regions of the UK. And then we extract the rainfall over those regions. And then we have a baseline period and a future period. So the baseline is our reference, and the future period we use to derive statistics of change to characteristics of rainfall. We calculate some thresholds that we have used to define what a heavy rainfall event is in the regions. And then we use that threshold to extract events from the rainfall series. So one of the things that we really wanted to do was look at what information there is in the rainfall projections themselves that goes beyond just what the intensities tell us. So to do this, we've created two sets of events. So the first one is taking the raw UKCP local projections themselves and applying this event identification method on those. So to do this, we have a lower threshold, which helps us find the start and the stop time of an event over a region. And then we also add a drain-off period of 6 hours. So the rainfall in a region has to be below the lower threshold for more than 6 hours for us to say that the event has been terminated. So we do this to make sure that we are capturing independent events in the time series. And then the upper threshold is the peak rainfall intensity of that event. And then we also created an intensity scaling approach where we created distributions of the rainfall over the regions and calculated the percent difference between the baseline and the future distributions and calculated like percent differences for the different percentiles of rainfall. And then we used those change factors to adjust the baseline rainfall time series to just account for the changes in intensities in the projections. And then we analysed how the frequency and the spatial extent and clustering of events changes between the two event sets to see what information we can find that seems to be lost when we only look at the intensities. And we created uplifts for the whole annual time series, so including all rainfall hours, and also separating the rainfall into the 4 seasons so that we could see if there was some seasonality to the rainfall intensity changes too. So one of the first things that we looked at was how the spatial extent of rainfalls changes. And so here I'm just plotted, or I'm just showing the results for winter short duration events. So those are events that have a duration of less than 6 hours. And so on the left-hand side, I've just created rainfall composites of all of the events for the baseline periods, the future periods, and then for the 2 uplift data sets. So what we see here is that the short duration winter events in the UKCP local projections themselves actually become much more intense and much more localised, with a higher intensity of rainfall covering a much smaller area. But this is something that the uplift approach isn't able to capture. And so this is providing us with some evidence that the UKCP local projections themselves are actually showing that there's a shift in the behaviour of short duration rainfall event in winter, and not that we simply just have more rainfall everywhere. And this is particularly important for flooding because winters on average are projected to become around 25% wetter in the future. And so if we have these really intense, localized, almost convective type storms embedded in these larger wetter winter systems, we potentially might see an increase in flash flood potential in the future in winter. And so I've also looked at how the summer short duration events changes too. So here we find that summer short duration events are to become, or they are projected to become both more intense and also more widespread. So here we find that there is a greater spatial accumulation of rainfall, and the centres of the events are much more intense, but also covering a much larger area. And we find that the intensity scaling approach is able to capture this magnitude, is able to capture this increase in intensity and size, but not at the same magnitude as the UKCP local projections. And so one of the things that we think might be driving this is that in the future, summer rainfall is becoming more organised and convective storms becoming more organised and larger. And yeah, so this is actually something that if we just use an uplift approach, we wouldn't be able to capture. And one of the other things that we've looked at is how events cluster in time. So in these plots on the left-hand side, I'm showing what the fraction of events that occur in 21-day clusters in the baseline and the future periods, with the blue representing the baseline, the orange representing the future, and then the black line is the uplift event set. And then on the right-hand side, I've shown what the cluster contribution is to the total seasonal rainfall. So what we find here is that for summer, we actually don't see an increase in the frequency of clustered events, but when events do occur in clusters, they are contributing much more to the overall seasonal rainfall. So this shows that there are potentially much larger systems, and this is something that the uplift approach is just not able to represent at all, because the way that we have scaled the intensities in the uplift event sets can't change the spatial or the temporal sequencing of rainfall events. So this is something that just isn't able to be captured using an intensity scaling approach, but the projections are able to much more likely are able to capture. And now I've shown same as the last slides, but this time for autumn. So for autumn, we actually find that the heaviest rainfall events become less clustered in the future, meaning that they just occur more evenly spaced across the years. And we hypothesize that this might be a shift in the event type of the most intense autumn events, potentially with more convective systems happening in autumn, with the summer season extending more into the typically autumn months. And again, this is just highlighting that this is something that intensity scaling isn't able to capture. And the clustering of events is particularly important because if we have lots of events occurring in close succession, this is likely to amplify flood risk. And so being able to capture these kinds of changes in any guidance that we produce for future flood risk assessments is being lost by just looking at intensities alone. Okay, so now that we've identified some interesting aspects of changes to heavy rainfall, what does this mean for flooding? So we have produced a test case for a pluvial flood model over Bristol and Bath, and we compare two event sets. So we have an event set of approximately 13,000 events that are taken directly from the UKCP local projections. And then we have produced some traditional design storms using an IDF approach and applying uplifts to those based on the same climate projections. And then we've forced pluvial flood model with those event sets to see what the differences are in the flooding over these urban areas. So the results were really clear, and we found that when we use the UKCP local rainfall as the driver of the flood models, we get considerably larger and more widespread flooding. And we actually find that the flooding amount changes about 20 to 50% compared to the traditional approach across all of the time periods that we've run. And the variability in that range is to do with the return period that was run. So we've attributed these differences in the amount of flooding to the fact that the UKCP local event set itself can preserve the spatial and temporal variability in rainfall events, whereas using a design storm, we're just using one uniform rainfall field over the whole area. And so it's not able to capture some of the more realistic aspects of the rainfall over the region. And so one of the implications of this is that it highlights that maybe what we use currently for surface water flooding to incorporate climate change into guidance is that we might be just misrepresenting things. So over this region, it looks like we're potentially underestimating future flood magnitudes, but maybe in other regions we might be overestimating. Like it seems like there might be a much more complicated picture than what we've currently been using. So yeah, that's an overview of our initial findings, but there's lots more work that we're going to be doing in this project. Oh wow, okay. So we're going to be scaling this up nationally first. So we're going to be, by the end of 2020, probably the early 2026, we'll have simulated 150,000 rainfall events through the pluvial flood model. And we'll also be producing some hydrological projections of how peak river flows will be changing. So we're going to be designing our hydrological analysis to look at some of these changes in rainfall that we've identified and what that actually means for river flows themselves. And then by the end of 2027, we'll have produced national scale fluvial and coastal flood hazard maps to go alongside these pluvial flood hazard maps. And then moving on in towards 2028, we'll be doing some more in-depth analysis into what it is about rainfall that is actually driving these changes in flooding that we're going to hopefully find, and be able to say something about that and provide some guidance, hopefully working alongside other people at the EA and at Natural Resources Wales and SEPA, who we've been in discussions with, to work out what it is that we can actually help to feed in with. So if anybody here has any ideas of things that they'd be interested in working with us, that'd be great to know. And so yeah, the main aim of this project really is to bridge the gap between high resolution climate projections and climate science with being able to produce actionable, real world usable information. Yeah, okay, I'm done. Much quicker than I thought.
Well done, Laura, that's perfect. And we have some time for questions now. So please raise your hand, and there's some roaming mics around the room. Go ahead.
I'm curious about your split of seasons. You know, the fact that you've split convective season into 3 different places. You know, you're looking at December, January, February, March, April, May. So the May goes with the June, July, August, September, and October. But you know, you've got autumn, it's got some convective events, and you've got your spring that's got some convective events.
Yeah.
So that's my first question, why you've split it that way. And the second one was why you've chosen 1981 to 2000 rather than 2000 to 2020. Because I think 1980 to 2000 is probably a fairly low frequency flood period.
Yeah. So
or maybe I'm mistaken there.
No. To answer your first question about seasons, is mainly just because that's the way that it's presented usually in publications. But yeah, most of the conclusions that we're drawing about the changes in the rainfall is to do with these like changing seasonality of rainfall in the future. And so I think coming up with a better definition of seasons that we can use is probably a really good step to add to our work, and trying to get like realistically it probably isn't going to be 4 seasons, it'd probably be more like 2 that sort of blend and change year on year. So that was probably a very unsatisfying answer, but that is basically the reason why. The reason we used 1980 to 2000 was, well, so I started this work like 2 years ago, and at the time the projections were released in 3 time periods, and 1980 to 2000 was the one that was covering like the historical period. The only other option we had was 2020 to 2040 or 2060 to 2080. So I could probably redo this analysis now that we have the full 100-year time series and use that more early 2000s period as a baseline. But I think the main aim of the work was to just have something as a baseline period, and all of the thresholds that we chose were statistically relevant to that time period. So we're actually just wanting to look at how things changed rather than choosing a baseline that was more, I don't know, like relevant to the actual time period that we're in, if that makes sense.
Yeah, just to add to that as well, of course, it's 1980 to 2000, but it isn't what we actually observed in 1980 to 2000. It's just the model representation of what's typical at that time. So even in reality, what events we actually got during that period, they won't have an imprint here. But any other questions? I have a question while people are thinking. So obviously we had that pilot study you showed, which was only looking at pluvial flooding. Do you have any sense of the relative importance of some of the differences in rainfall that you're identifying for fluvial compared to pluvial flooding? Do we anticipate it will have, you know, what we're seeing here will have more impacts on the fluvial side or the pluvial side, or is it very difficult to say?
So on the some of the initial work I've done looking at the hydrological projections, we're seeing quite considerable increases in the peak flows, particularly in the northwest and in the southwest. So I would assume that based on just, if we look at changes in peak flows, that will transfer to the fluvial too. So yeah, I think that they'll be considerably different compared to what we have now. And the magnitudes, so the flow magnitudes associated with different return periods, from just some of the initial analysis I've done. So like the 20-year return period in some of the river basins I've looked at changes to more like a 1 in 10-year return periods in the future. So yeah, these like much larger floods that we have seen in the observed records are potentially going to be much more common in the future.
A question, go ahead.
So with the probable change in the appearance of convection between now and 2080, do we think that there could be a benefit of running the computer models from an NWP perspective at differing resolutions to see whether the storms appear differently, when at the end of the, when pushing towards that 2080 period? Or are we confident that that 2.2 kilometer resolution is giving an accurate portrayal of what storms might look like when we get towards the end of the century?
You want me to answer
I was about to say, I feel like we have the actual expert to answer this, so I feel like we should let her do it.
So I guess 2.2 kilometres is a compromise between the best representation we can give of these sort of systems and cost. We did do a lot of testing before we ran UKCP local at the 2.2 kilometre resolution, and I can confidently say that we're doing, you know, the additional gain we might get to going to 1 kilometre today is very small. And of course, as you increase resolution, it's not a panacea for necessarily improvements either. So we tend to get far too many small storms as we go to really high resolution. I would say these models, which are kind of equivalent to NWP resolutions, are probably for some time to come going to give us the best representation we can.
Hi, thank you. I wondered about the clustering, something really interesting for floods, and whether this might be just the wrong question, but whether there's been, you could validate any of that at all, like say in the 2000 to 2020 period or something, just to know if what we're actually seeing on the ground in terms of clustering is like, yeah.
Yeah. So I think there's been a couple of studies that have looked at the winter floods in 2014 in the UK and trying to attribute how there was like many rainfall events occurring in close succession that really amplified those flood events. So there probably are some observed floods that we've seen in the UK that we can use to validate the results that we see. I think it's probably harder to validate like the rainfall, but the actual impact probably is an easier method to, or not an easier method, but yeah, like a more meaningful method to try and validate. Yeah, I hope that answers the question. Yeah.
Okay, one last question. Go ahead.
Yeah, I think my question is, once your study is completed, will that complement what the Met Office is doing, or will this be, the output will be an add-on from the results that will come out of it to add lots of other customers?
Well, the Met Office are partners in the project. So Lizzie is the PI of this project. So I hope that by design we'll be able to complement. But I also think like this is a research project as well. So I guess what we do is also to provide like scientific information from the project itself, but being able to incorporate end users in some of the decisions for the studies that we do along the road will help to make this more usable, I hope. Yeah, I hope that answers your question, but yeah.
Great. I think we should move on to our next speaker. Thank you. So our next speaker is Ben Wilding from Atkins Relas. Sorry, I don't know how to pronounce that. Atkins, okay, great. Okay, he works on nature-based solutions for both drainage and surface water management. He's led detailed design of sustainable urban drainage systems in Mansfield, Cardiff, Severn Trent, and is currently working on a scheme in Stockport. So it'll be really great to hear your perspectives on embedding sustainable drainage in planning and policy. Thank you.
Perfect. Right. Afternoon, everyone. Yeah, I thought I'd put a slide up where it's not raining, which seems to be most of the times I go out on site. The rain seems to disappear, and once we put these suds in, it seems to be blue skies, which never seems to go down too well. Are we changing? Cool. So I'm hopefully going to answer this question today. So how do we design cities for storms that we can predict, but we can't fully control? So obviously forecasting is improving every year. We can predict these flash floods with more accuracy, getting an increasing scientific base, as we've heard throughout the day so far. But fundamentally, we still have a system in the UK where we fixate on individual asset performance rather than thinking holistically as a whole system. So that ultimately ends up with pictures like we've got in the top left, the one with the cars in, which is the London flash flooding from a few years ago, just post-COVID. So we've got a system where we have gullies and traditional drainage designed for a 1 in 2 year, 1 in 5 year return period event, going into sewers designed for a 1 in 30 year event at best, all assuming perfect maintenance and that local authorities go out, clean the gullies and everything else. I live in Worcestershire. I can't speak for everywhere in the country. Worcestershire don't do it that well. Other councils might be better. I'm yet to find one, but I'm happy to be proven wrong on that. So generally, we've got this point where we've got these different design standards that don't necessarily go well together, and then the water has to go somewhere. And we don't really want it downhill into people's living rooms either. On top of that, we've got obviously climate change, global temperatures shooting up, storm events becoming more severe, so all of these flash flooding events becoming more likely. And we've got the other challenges going on in the water sector of sewage going into the rivers, drought happening, which is all effectively just different manifestations of the same problem, which is water not being where we want it to be at the right time. So flash flooding overall, from an engineer's perspective, has very much been the plan B. Historically, it's been that sort of, oh, we might think about that at the end, or trust us, it won't be that bad. And we need to change some of that narrative now to not make it plan B, make that plan A, and then start sort of weaving that in. So some of how we can do that is by using nature instead of trying to fight it. Constantly, if we try and make spaces, make places for water, look at where water's naturally wanting to go and not build a house right in the middle of a flow path, that tends to help us. So we have an overall ambition really to integrate these nature-based solutions as part of cities' DNA. We need almost this golden compass of when we're making decisions about regional planning, town planning, that we hold this sort of water management and where does water naturally want to go as part of that. On top of that, see, sustainable drainage can provide these wider sort of benefits, heat island mitigation, carbon sequestration, water quality. The list is fairly exhaustive there. So, how do we do it? How do we think about this as a system? So it's a mix overall. There's policy aspects, there's data aspects, which we've heard about so far today. There's design aspects, which are the parts that I mainly focus on. And then there's an educational piece. We need to get people on board. We need people to understand this sort of weird concept of risk and 1 in 10 year return period events and that side of things. So as scientists and engineers, we need to be better at talking to people, the big scary people in town hall meetings that are all convinced that we caused them to flood. And we need to stand up and go, during your 30-year mortgage, you are 50% likely to see this sort of event. So we've got a suite of options there. No particular sort of order in this cycle on the screen, but we need to look at what's an acceptable level of provision. We'll come on to some case studies in a minute, but we can't design for everything. No matter how much money we've got sloshing about, we don't generally have enough. So we can't always design to the biggest storm in the world. What policy do we need? There's a bit of a disconnect between sort of what policy says, what we have to do, what we should do. Policy drives the funding, policy drives other decisions. So we need to get in there and sort of influence that as well. And that's where the data sort of really helps. We need the facts. We need to look at what the sources of runoff are. Where are the big contributors? Where are flat roofs? Where are impermeable surfaces? Nothing really new there. Where does the flow naturally want to go? Where does it gravitate to? we know it goes downhill. That tends to be a good starting point. So what happens when it doesn't work? Where's the old bum moment? Where's that going to go? When the gully is not cleaned out for 5 years, where does that water want to travel to? And then how can we introduce some corridors to allow the safe conveyance of that flow across the land? We've got other aspects. What other benefits can we bring in? If we get more stakeholders around the table, we generally get a bigger pool of money to work with. We can solve multiple problems with the same answer. We have this weird thing of water having a red line boundary with various different stakeholders involved. Doesn't really work. That's where we're getting to with things like the Cunliffe review that's been published, in the sense of we need to pull people together. We can't solve exceedance management, flash flooding, CSOs, spills in separation. It needs to be seen as the same water management problem. Regional features, how can we control things on a large scale? Where water has gone down these channels, it's going to go somewhere. How can we slow that down to stop that downstream impact? And then what additional resilience measures are needed? Is that flood doors, floodgates? How do we manage that residual risk? And then we come all the way around to the top again. What's acceptable? How do we educate? How do we inform? So various examples from around the world of where this is done well or not. So Copenhagen, see, a bit more well established than a lot of other areas. So Trigger in Copenhagen, July 2011, 150 millimeters of rainfall in 2 hours. I was a student in Copenhagen at that time, and it absolutely fell down. I'd been there about a week at this point, and I was pretty convinced this was what the weather of Denmark was going to be like. So to still be talking about it 14 years later is slightly strange, but it caused £1 billion worth of damage overall across the city. I think the key thing as well is it highlighted that with a changing climate and this issue becoming more prevalent, Copenhagen wasn't ready. And most cities aren't ready because it's caught us out. We've sort of sat on our laurels for however many years and not really made these plans. So it's catching us out. There's a quote up there. I won't read it all out, but effectively there's a statement in the management plan that comes out and says, we can't design for every event. So what event do we design for? And if we can't design for every event, how do we manage that residual risk? How do we sort of safely control it as best we can with the resources that we've got? So flick through some of these reasonably fast, but effectively there's a whole mapping exercise where the flows want to gravitate through Copenhagen as a region, and then a suite of solutions that were proposed, including sort of fairly sort of large boulevards in the middle of streets that included sort of suds elements, green sort of swale type features to hold, slow down the flow, and provide that large regional control, that conveyance as well of the flows, as well as smaller sort of systems. Does this work? I'm going to break it. Yeah, so we've got these basins that creep up through the city. We've got green basins in Copenhagen that are double as football pitches, provide an amenity benefit, and change some of the story there. But we've also got bike parks throughout the city that also double as these storage areas. So overall, that's projected to have saved up to $60 million. I don't know what dollars, whereas the other thing was euros. But it's a progressive sort of change. And now through the planning systems in Denmark, that's caught up. And now there's more of a sort of view of how do we use this as business as usual. So it gets into the DNA. I'm going to skip Rotterdam. No, I'm not. Okay, I'm going to skip Rotterdam because it's very similar. I didn't realize there was music in it. So Rotterdam is very similar. There's some very large basins that have been introduced over the past 10, 15 years to provide that regional control benefit, as well as some amenity space, public pitches, various other sort of features as well. It's all about that regional control, slowing things down, making space for water. Coming a bit closer to home, I've always said that Edinburgh is probably a bit further ahead than most UK cities. My wife's Scottish, so I cringe every time that I say that, and say that Scotland's better than England on some things, but there we go. Edinburgh, we've taken a very similar approach to Copenhagen. So it's about embedding the lessons learned from each iterative sort of city and approach that we use, and then trying to use that to adjust to the sort of local conditions, but also embed some of that knowledge and best practice. Obviously, the modelling increases and the data increases as we go, so we can pull that in as well. So Edinburgh, we published the Sustainable Rainwater Management Guidance, which is the right mess to say, about 5 years ago now, and that's become quite a fundamental driver for how the city manages water overall. So Edinburgh's a mix of, see, a very old city, I'm not going to say how old, but old, built on combined sewers with loads of issues with surface water flooding, exceedance management being poor, and generally it just being a right mess hydraulically. So Edinburgh looks to sort of pull in, as well as where does water want to go, they wanted to pull in other aspects, UN Sustainable Development Goals, how do we embed 20-minute neighbourhoods, how do we get more active travel in, how do we try and solve this from a climate resilience piece, as well as a water management piece. So again, very sort of similar things to Copenhagen, wider waterways, green links, linking to active travel, trying to get away from this narrative of we need cars in the city centre all the time is generally quite a valuable tool. People often say there's no space. There might not be space if we want a 3-lane sort of highway through the middle of our towns, but if we take that down to 1 lane and put a cycle lane in, suddenly we've generated 3 meters of space maybe. And on top of this, there's sort of climate resilient schools, so it builds on a sort of educational piece. We're not going to solve this problem alone. It's going to take successive generations. So if we can get into the psyche of new people coming in, as well as that challenge of trying to attract people into STEM professions generally, we can sort of build on that. Thank you. So that is manifesting ultimately in projects such as George Street, which is an old photo, an old visualization, but will provide active travel routes through the city centre, as well as sort of rain gardens, tree pits, safe exceedance routing. And Craigleith is the bottom picture with the Suds swale there, taken a few weekends ago, and that was to help sort of manage some quite serious surface water flooding in that area. Conscious of time, so I'm going to skip through Stockport, but it builds on very similar principles. Key thing here is that Stockport is going through a regeneration, so there's ample opportunity at this point, sort of once in a generational, once in a 100-year probably opportunity to get water right. So we're looking at how flow paths move through Stockport town centre and how we can protect those through various planning mechanisms as we go through to help make space for water. And then various solutions that build on top of that, so green streets, additional surface water sewers to help resolve some other issues with combined sewers, and opening up some historic channels. I'm going to skip Nairobi. Okay, so project timelines then, overall. I'm sure everyone has a project that looks like this, with a few milestones in the middle, and everything runs smoothly and according to plan. At the proposal stage, probably. When we get into it, it probably looks somewhere like this, with various oh no moments going on, and oh, we should have consulted and we didn't, and why haven't we, and everything else. So if we take this sort of continuum, random yellow blob there, someone's clearly been at my slides. If we take this continuum, if we look at opportunities for nature-based solutions, making space for water, the further we can do it on the left, the better. That's where we see things as an enabler and an opportunity. What other benefits can we provide? What other problems can we solve? The more we get down here, it becomes a barrier, and we change the narrative from how can we make this interesting public realm that solves all these problems to how much you're joking, there's no room, we'll do it at the next stage. That next stage never really happens, by the way. So, some final thoughts then. Flash flooding, management of safe exceedance flows has been historically seen as that plan B, that sort of little sibling that we don't really worry about, and we need to sort of try and pull that to the front and elevate the importance of that through design. We do have an unhealthy over-reliance on individual asset performance. We fixate on this is a 5-year event, this is a 30-year event. We don't think enough about bigger picture, about how it works as a system. Water doesn't have a red line boundary as much as we think it does. If I can keep banging that drum until everyone is on board with that, I will die a happy man, I think. We still fight water. Fail to make places for it in our urban conurbations. We are changing that though through some of the case studies that I've been through. But overall, we need that whole systems thinking. Using nature-based solutions are good for enabling that, but policy, data, design, and education all have a key part. There is a very scary large version of me. If you want to carry on any conversations, LinkedIn, email, everything else. Any questions?
Thank you. That was really fascinating. If you've got a question, please put your hand up. I'll just kick off as the chair's prerogative. So I was wanting to ask you, how do you ensure that the designs are future-proofed? So they're resilient to unprecedented events of the future?
So I think it's the mix of embedding the climate change as normal into design, but then it's looking at overland routing generally and going, where do things want to gravitate to? So I think it's building in more of an approach of it's going to get worse. So where's water naturally going to want to go? And following that from source to sink or start to end, where take the water through that journey and try and sort of provide resilience measures as we go through. I think we're not going to get to a point where we can say that will be 100% effective for everything, but we can sort of go for a 100-year event, a 1,000-year event, this will be how it works. And we can sort of do stakeholder management on top of that and go, this is where water will pond, this is natural, this is where it won't, this is probably showing you've got a maintenance issue. So it's sort of how we bring people on board there, I think, as well. Okay.
Questions?
Ben, sorry, I missed part of that. Maybe you mentioned already we get to another event.
No, that's okay.
So I think obviously for the blue-green infrastructure or nature-based solution, multiple benefit, it's an important aspect. How could you ensure that's embedded in your planning and design?
So there's two sides to it. So there's various different tools out there. Syria Best is one that looks at multi-benefit analysis. Other options are also out there. So I think it's pulling that into a design decision. So we generally look at things cost benefit, and nature-based solutions can fall down when you don't do a full cost benefit analysis. So it's about looking across lifetime of the features, maybe that's 50 years, 100 years, and going, what's the carbon benefit? What's the water quality benefit? What's the benefit because you don't have to pump all this water somewhere else? So it's sort of embedding all of that in. And as soon as you start doing that, you can then sort of go, well, across the lifetime, it's cheaper by 20%, 50%, however much. So it's more trying not to get too narrow early on. And I think as engineers, we sometimes struggle to not go, blinker, that's the solution. We sort of have to think a bit, how's this still going to work when I'm retired? And yeah, go from there.
I actually have a question.
Yeah.
From the back. I always found it difficult to, given how modeling, rainfall, hydrological and hydraulic modeling is done for planning, I always found it difficult to prove how nature-based solutions provide a benefit. I don't think that they don't.
Yeah.
But I think that the way we calculate those numbers doesn't reflect the benefits. Do you have any thoughts on whether that's true or what needs to happen in order to actually realize those benefits in the sort of planning framework?
I think it's getting better than it was, but part of it is based on the data. So things like the Mansfield Flood Resilience Project that finished this year has now got 360 odd features, various sizes throughout Mansfield, a lot with monitoring on it. So there's that long-term, 4 years worth of monitoring data that will be gathered, and that can then be sort of re-fed into the models. I think we sort of think a bit too job done, put the suds in, off to the next project. But I think we need to sort of try and embed with various clients, whether that's local authorities, whether that's water companies, the need to sort of gather data on it, because that will ultimately help make designs more efficient and improve that evidence base. So I think it's an evolving piece. I think it's trying to balance the conservative nature of engineers wanting everything to be perfect with the empirical, it seems to be working, and trying to find a sort of good common ground. And the data is really the crux to that, I think.
Thank you.
Thanks for your presentation. Very interesting. But at the start, you said you were going to show some examples of where it was done well and some examples of where it wasn't done well. Were those ones where it wasn't done well ones you skipped over? Because I thought the message from those that you presented, it's all been done well.
No, I think generally they are done well. I think there are challenges in all of them. So if I think to Edinburgh, George Street obviously is a key sort of shopping street through, and main thoroughfare through Edinburgh. There's an issue that's gone on there with engagement with UNESCO about, not UNESCO. Who am I thinking? Yeah, it is UNESCO. Yeah, World Heritage Sites. Sorry. About trees on George Street. And we've gone round and round in circles about Georgians didn't have trees, apparently. Believe that or not. But that causes problems. That didn't touch on would be Mansfield, in the sense it was very good. It's delivered a lot of schemes, but ultimately there was a lot of resistance locally to it. So you end up with a bit of a disconnect between Severn Trent as the client, Mansfield Council as the sort of main local authority, and the local people. It was sort of skipped through, and everyone's going to be really up for this and solve flooding in Mansfield, until people realise that they're going to lose their parking space at the front of their house. And that tends to be where things start falling down. We started finding that people could get drop curb applications in quicker than a design for a rain garden in a residential street could be done. So I think it's more how that's where that education piece comes in. I think stakeholder engagement isn't necessarily seen as important as it actually is. If we can win people over to hearts and minds, that makes the rest of the project easier to do and ultimately realise better outcomes.
I have a quick question about your perspective of a lot of this, what you're doing is trying to retrofit as opposed to starting from scratch in a new development. So does that, I guess that poses quite a lot of constraints on what you're able to do, or?
There's more constraints, there's more complexity there. You're starting to deal with sort of layers of utilities and what space is available and different conversations around how does the street need to be used in the future, rather than if you start from the start and you go, that's where the water's going to go, A to B, we're going to protect that. That makes it easier. It is a bit of a mess when you try and retrofit these things, but there's a lot of learning that you can take from that retrofit approach back into new build, and we're building new houses everywhere. There's more SUDS guidance, there's more requirements, but it's trying to sort of still follow those same principles and not shortcut it just because it's new development and maybe easier.
Okay. Time for one quick one. Yeah.
Just to say that before 2012, there was no requirement for anyone to maintain a record of pluvial flooding. So, you know, if you get an event, people think, this is unprecedented, and then we respond to this unprecedented flood. But if you look historically, you discover that there were half a dozen of these events that were actually bigger than this.
Yeah.
And I've done that for Newcastle.
Yeah.
And I found that, you know, there's the place that was flooded in 2012 was also flooded 5 times over that previous 200 years. So, you know, you need to look at historical events as well as what you've experienced recently. And also, there are lots of places now where they've not had unprecedented events in the last period of years, where if you look historically, you'll find that things have occurred where you will give you good information as to where the problems are likely to be.
I think I was speaking beforehand when we was all arriving and saying, in my view, some of the problem with the UK is we don't really flood enough. It sort of, that's a controversial thing to end on, isn't it? But it falls out of the public psyche. It falls out of people's awareness. If we flooded every year, we would do something about it. Maybe.
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 Positive note.
Yeah.
Let's move on. Thank you. Okay, we now going to move to our final speaker of the session. So Professor Liang is Professor of Water Engineering at Loughborough University. He's also UNESCO Chair in Informatics and Multi-Hazard Risk Reduction. So he spent his career developing and applying numerical models to address disaster risks. So this is not just flooding, but also other natural hazards, landslides, debris flows, tsunamis. So yeah, thank you for joining us.
Thank you, Lizzie.
I'll give you 5 minutes.
Yeah, thank you. Because I'm not very good at keeping the time, so I think I'm going to keep a look at my phone. So yeah, hopefully I think I can finish this, you know, in 20 minutes. Yeah, I think it's great, you know, to place the talk, you know, now because, you know, after, you know, in the morning we heard about, you know, I think what we can do, what the challenge, you know, on the sky, and then in terms of the weather forecasting. So now I think it's a time to talk about, you know, what we can do really on the ground and in terms of modeling this kind of, you know, flash flooding. So my talk is just basically, I think, trying to show, you know, I think what is the latest technology and model high-performance computing and also potential AI machine learning can really do in terms of, you know, modeling the detail of flooding at the same time and trying to manage the risk. Because, you know, I think I think probably it's a general company, you know, I think recognize that, you know, I think there's no simple solution to this kind of event. So I think we really need to do a bit more. So I think this shows, you know, I think what I'm talking about. So flooding, obviously, we all know is one of the most widespread, it's not the one, I think, natural hazard across the world. And also, I think more importantly, flooding, when it happens, it's not really pure water, right? I think it comes with lots of other processes like, you know, a soil erosion, and then like, you know, I think I hope, you know, I get the environment. So showing here, you can see that lots of, you know, I think cars and floating debris, and I think we move and really drive along by this flow of water, and then interact with infrastructure like bridges, and then cause, you know, damage, and then, you know, I think change the story of the flooding. So I think So for that reason, and also I think even more to mention, it's like the human activities, because I think now the common practice of assessing risk and managing the risk, especially, and also modeling flooding, is assuming we have a static society. That means we have the data and set up the scene, and that would not change throughout the simulation process and also risk assessment process. But in real world, that's not the case. Like I think Adrian mentioned in the morning, because people do lots of things in between. I think the government are going to do I think emergency management, and then people can manage the risk themselves. So that would change all the exposure and the vulnerability, and also the flooding dynamics. So I think we don't really take that into account directly, at least. So for that reason, we really need to develop tools so that we can really understand more, and also trying to arm ourselves or equip ourselves to really to manage this kind of risk and complicated I think processes and and other procedures. So I think our team, so I think in the last 20 years, and then trying to I think develop these kind of tools. So I think now I can't really have time to go deep into that. Basically, we develop this kind of modeling skill. We call it hydrodynamic model. So you heard lots of modeling. So I think I appreciate not everybody coming from the computation hydraulic side. So I think the kind of model we develop is a really I think trying to simulate what I think flooding happening from rainfall and down to inundation, taking into account all the dynamic detail in between. So I think take into account fully the for example momentum conservation, mass conservation, those kind of physical laws. So rather than the simplified model. So I think so this type of model, normally is now I think we consider is the best model available for flood modeling. I think in terms of the accuracy, reliability side. But the trouble is, I think this kind of model come with the cost. The cost. That means, computationally extremely expensive. They do not normally, I think apply, in the real world in the past. So, but luckily, I think back in about a decade ago, I think more than decades now, 2010, something like that. And then we called, we have the kind of technology, so-called GPU, graphic processing unit, and then that brought into scientific computing, and then that changed, the whole computing, I think landscape of that. So I think our team also developed this kind of technology, and then make this kind of model, I think can be applicable to the whole city, a whole catchment of thousands of square kilometers, but at meter level resolution. Like I mentioned before, the model, flooding is not only flooding. So that's for that reason, I think like Lizzie mentioned, I think we also look into, other process like rainfall can also induce landslide and then, cause flooding. At the same time, that can, cause erosion and evolve into debris flow. And then that, the flooding can also carry cars and other floating debris. So I think this is kind of very complicated, process. So, and then we also are going to mention later when we also, couple this kind of thing, with a human system, to look into interaction between the natural process and also the human activities to see how we can really take this whole system thinking, like mentioned by Ben, into consideration when we assess the risk of flash flooding, at the same time manage the risk. So the model I think now is kind of quite widely recognized. So we also won I think some prize for that, and also EA classified it as as one of the good example of how the research investment lead to some impact. Okay, so the model called HyPIMS, I forgot to mention that in a high performance integrated hydrodynamic model system. So I think we call it HyPIMS. So because again HyPIMS I think computationally very efficient after we embed it into high performance computing. So then we think about whether we can really use HyPIM to change the way we simulate, for example, fluid flooding. I think that's what we attempt about 10 years ago. So. And then in the past, when we look into fluid flooding, we have a suite of models, from hydrological model, I think predicting the hydrograph, out of the catchment, and then link to the, for example, river modeling, and then translate the hydrograph from upstream to downstream, and then couple with inundation model, and then to look at the impact. So I think in here we try to really use rainfall only to drive the whole process of flooding, from for a whole catchment, from rainfall, runoff, overland flow into river, and then I think converge together and then impact for example cities, things like that. So that's what we did I think using this kind of framework So again, just, rainfall, drive the whole process, from rainfall and then down to inundation. So this is what we did, I think in terms of applying to Carlisle or Eden catchment wider. So we produced the 2015 Storm Desmond, induced flooding. So I think for the whole catchment of 2,500 square kilometers, and then we use 5 meter resolution. So basically 5 meter times 5 meter, we got, the temporal, spatial change, velocity and also water depth. And in that level, and then we simulate the whole process. So I think this is some of the results we show. Basically, I think showing, I think some good, result. So I think this is what we can see. I think the whole catchment, you can see that, after rainfall happens, and then that's, how the catchment respond, to the rainfall, and then all the water converge into, the river, and then going downstream, can't see them, and then flood at Carlisle, like this one in here. So the red line is the outline of the inundation, I think surveyed by EA, and then trying to compare, I think our result with that. So this one actually, it's we further, I think, improve the model, for forecasting by integrating the model with the Met Office numerical weather forecast. So I think to trying to see, whether that's feasible, basically. So I think with the Met Office weather forecast, we release 36 hours in advance, and then we simulate the whole event again from rainfall down to inundation. We only need to use less than 2 hours to finish the whole simulation. So that means, I think this potentially can be used for, I think forecasting, and it gives, substantial lead time, I think, for forecasting such a kind of event. So don't forget this, we did this, I think about 10 years ago. Now the technology do much better. So I think probably, similar to the whole event using the GPU nowadays, we use less than, I think half an hour for that. So yeah, for all the detail, I think that's in this paper. So I think, again, I don't really have time to go down into details in here. Okay, so I think importantly, I think I just trying to show in here how we can do better in terms of, I think, again, responding to this kind of flash flooding. Because, I think in real world, people, will have all the actions. So I think organizations and individual, people and also I think for example traffic, that really interact, I think rapidly with flooding. So this, how we trying to, develop this kind of, couple human and natural systems model. So basically, it's a use the I think I got, I think something in here. Okay, going back. So I think basically, so we try to use, I think the HiPIMS, the model I mentioned just now, and then simulates the natural process, like just basically rainfall induced flooding process. And then that, fully coupled with the so-called agent-based model, so that to simulate, I think organizations and individual traffic dynamics and things like that. So I think all of the agents that can be defined, again, as a different, different type, and then they have different roles, and then they can interact. So I think it can be also embedded with the, for example, AI, the the reinforcement learning, and then to help this agent to make decisions themselves, to optimize, I think what they can do, in helping, for example, the organization making the decisions. So I think I'm going to show that, in a bit later on. So I think again, for the natural process, and then we use HiPIM to simulate that. And then for the human subsystem, and then we use agent-based model. So I think this is more or less showing, how agent model would work. So I think the little dots in there, and then representing either individual or car. And in here, it's we're trying to show, for example, in a flood event happened, and then how the cars and also, I think individual people respond, to the warning, and also what they see in the real world, and then they quickly run into a shelter. In this spot in here, so that, I think here, obviously, we want to test, whether the shelter, I think should be properly, located, and then so that people can, and go to that, safe place in real time. So I think people say, oh, wow, why don't you put it in high ground and the shortest distance? But in real world, not like that, because now we have traffic, and then the shortest distance may not be the best one. So I think this kind of tool, can really helpful, can be really helpful, to simulate different scenarios to help making decision. Okay, so I think for this kind of system, I use a few case study to show what it can, what it can do. So the first one, it's we trying to assess the flood risk. So I think in the past, again, when we assess flood risk, we are assuming a static society. So in here, we try to, to make, people actions. So in here, using the Eden catchment again as an example, and then now we don't really like only simulate flooding, we also simulate the household, actions. So when they receive warning or see the flooding of flood water rising, and the household can make decision, they can take action to mitigate the event. So that, for example, moving valuable to upstairs and then move their car and things like that. So in here, we try to, simulate that kind of, I think a scenario in here. So I think all of this, obviously for the agent-based model, we know that, they don't really make, this deterministic decision. So in here, it's a kind of probability-based model. So for example, a quick one is that, so if a household, feel by the senior people, just old people, and also children, and also maybe, people with illness, and then they are more willingness, not to take action. So 95% of this kind of household would not take any action because they don't have the capability. So I think, for that, but this number is not, I think created by ourselves just from the literature, I think, past research. So put all of this into consideration, and also, from EA's, report, I think about 63%, 62% of the household receive warning, in this event. So we put all of this, baseline, information into the simulation, and then we simulate event. So I think to show, whether, I think taking into account this kind of, household level, decision, and then that can reproduce, the damage as we kind of, I think provided by the government report. So this is a number. So basically, I think the number is within the range. We don't have more detail, I think obviously information to validate the model, but seems like the model doing the right thing. And then in here, it's trying to show, I think, different scenarios. For example, like just now, I think the warning may have a kind of good impact in terms of mitigation. So in here, we show that, if, I think the warning, I think, again, in the real world, about 62% of household receive warning for this event. If all people, all household receive warning, what would be the result? And then if, all, receive warning and also respond, for example, I think I think Ben mentioned, if, I think people, the awareness increase, they're more willing to, respond. If all respond, and then what the consequence will be. And then if, I think, there's no warning, what would be something like that. So I think we do the comparison. So I think to see, if, the household, receive warning or respond, I think that can, create lot, I think substantial mitigation in terms of loss. So that, I think that information could be useful for the government, for example, and then invest in education and then improve the awareness. Okay, I'm getting there. Okay, so I think for this one, it's also another interesting one. So I think we know, AA, for some of the a town or county, they maintain the sandbag. I think people can apply for sandbag to protect their house. And then, I think sandbag normally can protect, up to, for example, 30, 40 centimeter of, flood depth, I think something like that. In here, we simulate, I think the event, I think household can apply, for sandbag. And then obviously, depending on the flood dynamics, some of the area would be effective, some of the area would not be effective. So I think in here it's showing, for example, in this area, that's where the figure, I think in the west, that means the most effective area. So showing the effective area. So this area would not be effective. So I think because the flood water may just exceed 40 centimeter of the height, and so that I think for this information also important because with limited resources, and then the local council, for example, can have the information where to put the resources for sandbagging, for example. And then for those areas, and then we can use alternative, for example, like the temporal flood flood defenses. So for example, now widely used is the temporal flood defenses. So I think that's I think in the UK as well. So in here, we also test a few scenarios. So I think if we select a few places according to the simulation result, and then those areas could be most, I think, protected by the temporary flood defenses, and then what can happen? So I think we also simulate a few scenarios. So this is the first scenarios. If we design 4, I think temporary flood defenses, and then have the warning, we all install into the ones. So I think this is the area, that the orange area is the properties or area protected by these temporary flood defenses. But sometimes, I think we don't really have the warning, or, I think the warning may not, ask us to action. So for this reason, and then sometimes we also need to make real-time decision making. It's so that, I think according to, to the flood dynamics, and then the local authority make decision in real time. So, okay, we need to install, I think temporary flood defenses in certain area. So if we're making real-time decision, I think two of these defenses would fail. That means, the flood water going to, for example, increase, I think too quickly or moving too fast, and then to threat the life of the engineer installing the defenses. So that cannot be successful. And then, only those two, I think successful, and then protecting a certain area of the domain. And then the last one is like, if we have limited resources, can only install one, I think defenses, and then where it goes, and then we can simulate, different scenario, and then choose the one most appropriate. Okay, finally, I think the final, I think scenario is nowadays also we use a lot is the mobile pumping station, especially for the urban flooding. So I think traditionally, I think we send the mobile pumping station to location where it's low lying and have the kind of accumulating water. But then whether that's the most I think appropriate place, we don't really have the data or model to infirm that. So in here we try to use the AI reinforced learning. And then so that, I think to train this kind of, I think agent to make the decision for themselves, so that, not, going to the lowest location, immediately, and then, but they can plan and schedule, the road and also the time of pumping, themselves. So in here, the decision-making process is that, I think we have the high-level government agents, and then they send, I think the agent, to a bigger area, because that can be designed according to experience. And then the agent, I think the pumping driver, or the executive executive and then they can make decision in this kind of small area, and then where to go, and how long they stay, or something like that. So I think this is the what we did in here. So this is a case study in Can Tho, Vietnam. So this is how it goes. So I think the agent can, I think after train, for example, with 1 year, 1 in 10 year flood and a 1 in 20 year flood, pre-train the agent automatically make decision, and then they can do the job themselves. So this is how it works, I think in the modeling. But the quick conclusion from this study is that I think depending on which period of the event. So for example, when the rainfall is ongoing, and then going into the lowest location would not, would be the best. Because, I think, when you go to lower location, water keep on, coming to lower location, no matter how much you pump, and then you would not affect too much the width. So then, but after the rainfall, and then, I think going to the lowest location, that could be quite effective. So I think this is a main conclusion coming from, I think the study. Again, this kind of information, it's really, I think, kind of useful for decision making and and also emergency management. Yeah, this is the last one. Yeah. So so basically, I think running a bit I think fast at the end. So in here, I just trying to show, I think, what is the technology side. I think, again, high performance computing and machine learning can do in terms of telling more detail about I think what happened on the ground after the rainfall comes to the ground. So I think in here, so I think the possibility of the technology can do much more. So I think, but I appreciate I think all the challenge mentioned by I think Stephen, and also I think agent in the morning. I think sometimes technology, and we also facing lots of other things. So I think for that reason, for me, I think I don't want to read through all of this, just summarizing what we can do with the technology. I think I like this in here. So I think for that, and then we really need to have this kind of transdisciplinary collaboration from different discipline, and also I think collaborate with I think people from different sectors to move this this field, important field ahead, because I think like we listen in the morning, I think I think different field have different challenge and different in technology. So I think doing that, and then we can really make use of the best technology or best approach I think into this practical operation. Thank you very much.
Okay, thank you very much. And I thought rainfall projection was hard. So we have some time for questions. So while you're thinking, I'd like to ask, what do you see as the first order uncertainty?
I think, like I mentioned, I think the first order uncertainty, I think if for the flood modeling side, I think it's coming from the human activity because are highly uncertain and also data, obviously we all know that, but I think that's getting better and the data side is getting better. And that's what we believe, from the technology in terms of, data, collection, things like that. But I think wider is coming from this because this outside from my field is that's the reason why I asked the question for Stephen in the morning. I think probably it's from a weather side because it's especially for fresh flooding forecasting this kind of highly localized connected storm still a big challenge. So I think for the water, I think prediction side that can be done, very accurate now. So in modeling, simulating water flow. It's provided the data. I think, for example, the topography data is correct. I think that's I think much less challenging at this moment. Yeah.
Hiya. So how would you sort of think about balancing like model resolution, model complexity with sort of the uncertainty in all the inputs when you're looking?
Talking to the top of it.
It's still working, yes. So how would you balance model complexity, model resolution with sort of the uncertainty of all the inputs that are coming in your hydraulic model?
Yeah, I think again, the data side, I think now the model result, I think it's more uncertain against the data. Yeah, because you can imagine that now, even the, for example, the topography, we, I think for hydrodynamic modeling, we use, I think that's a kind of important data set we use. We still have about, 10, 15 centimeter of uncertainty, even from the latest LiDAR. So I think that's, kind of level uncertainty when it coupled into, I think the modeling that would create lots of, I think different stories. And also, especially when we look into urban area, because that's, human activity, impact a lot. For example, drainage system. So, now, lots of cities, do not have a drainage, data. I always say, even you have that, are you going to believe that? Because, I think drainage system that, some of them built, I think 100 years ago, and some of them even built latestly, but and a lot of extension, and also, under the ground, and then a lot of story happen. You got blockage, and things like that. So I think all of those, I think can really like, affect the reliability of the flow. But good thing is that now we have a lot more observations. So I think observation is not really coming from traditional way of I think scientists going out to take a measurement. It's coming from, for example, the crowd source like the photos, video, CCTV, all of those give us more detail in terms of the flood story, and then we can use that to for example to really calibrate better the model, and also I think for example using the machine learning and then to really do some real-time adaptation of the parameter to make the simulation more accurate. So I think the technology again can do a lot, but I think I think all depending on I think how we can use it. Thank you.
Hi, thanks. My question is kind of how far away are we from establishing these digital twins? So having this, pulling together what we've seen today, having forecasting coming into the mayor's office in Canton, for example, and then in real time deploying pumping systems or temporary defenses. Is that actually happening, or when will it happen, and why isn't it happening? Is it funding, and what are the challenges there?
Yeah, I think that's a very, very good question indeed. So I think from the technology point of view, this is feasible, achievable. So actually, I think before I came in, the reason for me to miss 1 hour, it was was because I chairing a webinar done by a colleague from the Tulane University in the United States. So he shows how to build exactly what you asked him. I think the digital twins. I think to manage I think flash flooding. I think using AI. So and then also coupling with this kind of technology. So what they did is that they've gone much further than this. So they started to use I think the kind of agentic AI or the large language model, and then to really like extract information. I think building this kind of interactive I think agent to help I think connect this model and also the real world I think data together. So I think the big challenge in here, it's apart from, I think people, different, people from different field working together, it's really like the so-called disciplinary collaboration. I think working with, for example, the government agency working in the field, for example, for Focus Center, EA, and then how to really like, communicate so that make sure this kind of, I think technology can be tested. And then, I think to really deal with, this kind of non-scientific, issue and then put it into operation. I think that's probably, for me, that even a bigger challenge than technology development.
Hi, thank you. I wondered about validation. I see it for the HiPIMS model. So you've got kind of conventional model chain, if you like, and then that one. I wonder, have you done a direct comparison of the two in the same place, or just any validation data, or some of this agent-based stuff? Is there any validation sort of it?
Yes, indeed. I think lots of validation being done because timing. So I couldn't really show in here. So I think HiPIMS been applied because of open source model. So I think I did, ask a student look into the literature. So I think more or less now, more than 40 countries, across the world use the model for flood modeling, forecasting, or risk assessment. So there's lots of, I think assessment. I think, apart from our own group, in our own group, I think we apply, the model, to the UK, China, Nepal, and different area. So I think compare them with, again, like the direct, I think a survey, for example, done by EA, the flood, I think inundation outline, and also the river gauge, I think, kind of dynamics like I show in there, and also important for urban area, like, the one we did in Newcastle. We used the published, I think, photos. So I think we got hundreds of them. And then to compare, I think, where exactly flooded, and then to see whether, the simulation result, I think consistent with those shown by the photos. The good thing about now is that, every photo, they got the geolocation and also timing. And then you can easily see, I think, I think whether, I think the same result at the same time, same location, whether they're consistent.
And was it quite different from the conventional modeling results?
What do you mean by conventional?
So you had the conventional modeling chain on your slides with the hydrology and then the hydrodynamics, and rather than the kind of the rain falls straight in, sort of rain on grid, I guess, basically, in the HiPIMS. I just wondered if you'd done any direct comparisons to see which compared better or which validated better against observations, or
we didn't do this kind of transmodal comparison. The reason being that I think the simulation we'll be doing here have a different purpose. So for example, the traditional hydrological model, they don't really give the details, of how the water moving around. So they can give, I think, for example, indicate, the hydrograph and also water level and things, and then, use that, to assess the risk. In here, we more, I think, simulated in detail how the water evolving, from rainfall. So I think it's a different type of modeling approach. So I think it's a really difficult to comparison. But I think one thing is that, for this kind of, highly localized convective storm produce fresh flooding, because that's I think the dynamics is highly transient. That means changing really fast. So I think in order to simulate this kind of, I think a process accurately, reliably, we should use this kind of highly dynamic model, full dynamic model, and also embed it with the so-called shock capturing approach numerically. So that means the model can be, used to simulate this slowly varying flooding process. At the same time, can simulate this a very fast, evolving flooding process, like induced by dam break, tsunami, and things like that. Because this kind of fresh flooding, they can have a localized, I think, very dynamic process. So we should use this kind of modeling approach to capture, I think that. Yeah.
Thank you. Brilliant. Okay, I think we better draw it to a close there.
Yeah,
really
thank you.
Fascinating. Thanks to all the speakers.
Hope everybody's refreshed. We've got a slightly different format for the end of the day. We've got a series of speakers who are going to speak for 15 minutes each, and then we're going to have a panel discussion for 25 minutes afterwards. So So we'll look forward to an informal discussion, lots of joining in. I'm Joe Pierce. I'm the new president of the British Hydrological Society. I'm going to carry on sticking to the theme of sticking to time. And with that, I'll introduce first speaker, which is Dr. James McKenna from Newcastle University. He's a research associate in hydrodynamic modelling and his research is primarily focuses on the development, validation, and implementation of novel numerical models for simulating fluid dynamics. Most recently, his work centered on the use of machine learning techniques to optimize flood interventions by leveraging CityCat, a state-of-the-art hydrodynamic flood model developed at Newcastle.
Hi everyone, and thank you for the opportunity to be here today and present to you all. Thank you as well for the introduction. My name is James McKenna, and as mentioned, I'm a research associate in hydrodynamic modelling at Newcastle University. The topic of this presentation concerns recent research that I've conducted with my colleagues at Newcastle on the topic of automating the design of urban flood interventions. With the growing threat of extreme rainfall events, which is being exacerbated by climate change, there's a real requirement for the development of flood-resilient urban centres. And with the contemporary shift towards nature-based solutions, the concept of blue-green infrastructure has emerged as a promising solution to this problem. And you can see on the slide some nice examples. Traditional approaches to designing flood interventions involve having an engineer use their expertise and some appropriate design or modelling software to iterate towards a suitable design for the client. Whilst this process is tried and tested, it's slow, expensive, and of course, it's susceptible to errors in human judgment. Therefore, our proposed approach with this research project was to develop an automated approach that would enable decision makers to explore a wider range of potential solutions and achieve better outcomes. Our chosen machine learning technique was the use of evolutionary algorithms. And we chose evolutionary algorithms because they're highly effective at searching the sorts of large discontinuous search spaces that you'd expect for these types of problems. And they can do so whilst maintaining a diverse set of solutions. As the name suggests, evolutionary algorithms use evolutionary principles like survival of the fittest and natural selection to guide an iterative search to a set of high quality solutions. Formally, we use our evolutionary algorithm to solve a minimization problem. Specifically, we're considering bi-objective minimization problems involving the cost of implementation of the mitigation strategy against an appropriate flood risk metric. For the flood risk metric, we've implemented two different metrics that can be measured. The first is the expected cost of damages due to flooding, and the second is the number of buildings classified at high risk. And of course, depending on which objective is selected, the optimal solutions will change. So as you can see here, I don't think the laser, it's working. We've got an objective space here, which contains solutions marked by crosses, and we're aiming for our algorithm to find us the set of red solutions referred to as the Pareto optimal front, which represent the solutions for which a given cost has the minimum flood risk. A key aspect of an evolutionary or genetic algorithm is the genetic representation. That's to say, the way in which we encode candidate solutions in a way that's compatible with evolutionary search operators. Within the language of evolutionary algorithms, we refer to the genetic encoding as the genotype and the physical manifestation of that genetic encoding as the phenotype. In our case, we use binary strings, like the one you can see here, to encode our solutions, where the long binary string represents the entire solution for the whole catchment, and it's made up of smaller binary strings which represent the individual features which are to be implemented within the catchment. For the individual features, we've also implemented two different feature representation styles. The first of which we refer to as a zonal feature. And this enables us to effectively optimize the placement of features within the catchment by either excluding or including features within pre-delineated zones within the catchment. The second feature representation style is more complex and allows us to optimize the individual characteristics of the features themselves. So for example, with a detention basin, we might want to optimize the depth and the area. And of course, this can get more complex as well. In order to evaluate the effectiveness or the quality of each candidate solution, a decoder is used to interpret the genetic information and produce a representative hydrodynamic simulation. From the results of that hydrodynamic simulation, the cost of the strategy, as well as the associated flood risk metric, can be evaluated, and therefore we have a comparative basis to determine the relative quality of the different solutions. Of course, since we're required to run a hydrodynamic simulation, or maybe many, per candidate solution, it's prohibitively expensive to evaluate many solutions. However, it's important to note that fully dynamic hydrodynamic models are required when our objectives are concerned not only with the extent of flooding, but also local estimations of flood hazard or vulnerability, which is what we really care about in this case. In our case, the hydrodynamic component of the tool is CityCat, which is developed by Vasilis Klenis at Newcastle University. However, alternative fully dynamic models would be appropriate, provided they can also explicitly represent the features which you wish to include within the model. Since there's an unavoidable expense involved in the evaluation of each candidate solution, it is therefore necessary to implement an evolutionary algorithm which minimizes the number of hydrodynamic simulations required to find a set of high-quality solutions. And that's what we've done here with our proposed algorithm, which is referred to as an epsilon multi-objective evolutionary algorithm. To validate the performance of the algorithm, we performed some validation test cases using a catchment surrounding Newcastle University and compared the performance of the algorithm with benchmark well-established evolutionary algorithms. The first test involves a simple problem which has known solutions, and therefore we can determine A, whether the algorithms are able to find the exact optimal solutions, and if so, how quickly they can do so. The second test involves a more realistic problem, but the search space is intractable, and therefore we cannot know the exact solutions, and only inter-algorithm comparisons are possible. Here you can see the setup for the first validation test case. We divide the catchment into 12 zones and consider the implementation of permeable paving as a zonal feature. What we considered here for the implementation isn't particularly important, but that's what we used. Since we only use 12 zones, the search space consists of a total of 4,096 potential combinations, and that number is small enough that we can do an exhaustive search and see what all the solutions look like. And here you can see a plot in the objective space of all 4,096 different combinations. What we're aiming with this test to see is whether our algorithms can find those optimal solutions highlighted in red, and if so, how many hydrodynamic simulations are required to do so. Here you can see animations of the progress of the respective algorithms as the number of simulations increases as they're evaluating different candidate solutions. On the left-hand side in red is the proposed algorithm, and on the right-hand side are the benchmark algorithms. Hopefully what you can see is that the coloured markers are converging towards the known optimal solutions, but that the progress of the proposed algorithm is much more rapid than the benchmark algorithms, and there's a far superior spread in terms of the results. In fact, if we look at plots of the convergence, where we have here on the y-axis a measure of convergence where 100% is exact convergence to the solutions, and on the bottom we have the number of unique hydrodynamic simulations required to achieve that, we can see that all three algorithms do converge to the optimal solutions, but that the proposed algorithm converges much more rapidly. For the second case, we use a more realistic scenario in which we divide the catchment into 100 zones for which we consider the implementation of permeable paving, and then we also include the implementation of 4 detention basins modelled as local features. In this case, the search space is so large that we could not hope ever to exhaustively search it, and therefore we don't know what the true solutions are, but we can compare the performance of the algorithms. Here we can see the progress of the algorithms as, again, the number of simulations increases. Hopefully you can see that the proposed algorithm, shown in red, produces a far superior set of solutions with respect to the alternative algorithms, with obviously the solutions closer to the origin being better. And in fact, if we look at the absolute convergence, we can see that the number of simulations required to reach the same convergence point is very, very different. So for our proposed algorithm, we only needed 25 to reach that level of convergence, whereas we needed several hundreds for the other two. And this is the same as we look at different convergence points. And obviously in practice, this is very important because that difference in the number of simulations required represents time savings of days, weeks, or months, depending on the size of the catchment. And if we're going to use this in practice, then that's of utmost importance. If we compare the final solutions, in this case, we terminated the algorithm after 3,000 hydrodynamic simulations, which is just an arbitrary cutoff point. We can see that the proposed algorithm has a really nice spread of solutions, which are far superior to the benchmark algorithms. In fact, in the most extreme cases, we're able to find designs which are £20 million cheaper that offer the same flood risk. Once the algorithm terminates, flood maps are then produced for each of the solutions within our optimal set or approximated optimal set. And then decision makers can then use these to make informed decisions on investment based on their own requirements and criteria. So to summarize, the presented optimization tool provides a step toward automating the design process. The algorithm is specifically designed to minimize the number of hydrodynamic simulations required to obtain a high quality set of solutions such that it's usable in practice. After the algorithm terminates, decision makers are presented with a set of solutions which they can choose from, and it offers flexibility for them to make their own trade-offs between cost and acceptable risk. And therefore, for example, if a local council has a set amount of money to spend, they can say, okay, maybe it's actually better to go for this option based on the presented results. Thank you very much for listening.
Move straight on. Dr. Samuel Ramsden from the University of Leeds, if you'd like to come up, thank you. Dr. Ramsden is an Impact Translation Fellow for the Integrated Catchment Management Solutions Programme. It's supporting the West Yorkshire Innovation Programme and managing research projects, including flood early warning systems and communities, and unlocking policy support for nature-based solutions. Sam.
Thanks very much. Hi, everyone. I think this presentation is a bit different because it's not focused on a model and model development. So basically, I'm presenting on the West Yorkshire Flood Innovation Programme and some of their projects, particularly around flood early warning systems. And it's a really active partnership of the different flood risk management agencies in West Yorkshire. And then we support them as the University of Leeds as well. And basically, the programme is adding value to the kind of core flood risk management responsibilities of lead local flood authorities. And it's meant to be kind of innovative products that help them respond to flooding and prepare communities. Yeah, so basically it grew from a failed FCRIP bid, but they felt there was good value in kind of continuing the partnership anyway and trying to develop their own projects. And so that's what they did. And we're approaching our 4-year anniversary, and we've got around 2 million in funding, and we're strongly supported by the Regional Flood and Coastal Committee, which is a really important source of funds. And then we've got kind of 5 key themes, one around SUDS and blue-green infrastructure, nature-based solutions, property flood resilience, community in the voluntary sector, and that's focused on mental health and trying to reduce the mental health impacts of flooding. And then focusing for this presentation is on kind of enhanced flood warning systems, flood early warning systems. It's not kind of formal integrated systems, but really where we can find projects that add value to the kind of standard flood warning systems from the Environment Agency. So particularly looking at surface water flooding, smaller tributaries, maybe helping some communities in more rural areas that aren't served by flood defences. And we, as I said, we're pretty active, so we have monthly board meetings with the lead flood risk managers, Yorkshire Water, Environment Agency are there as well. We have a large steering group including civil society. We have an annual conference which is coming up on the 24th of November. And then we also meet weekly with the Leeds flood risk manager, who's really kind of dedicated. So that's quite a big commitment from him, because obviously Leeds is a big local authority with kind of many flooding issues. And so these are some of the projects that we've kind of covered. I'm going to go into detail on two of them in the time allowed. So one of them is, we did some research around the use of flood early warning systems by communities, and kind of passing on best practice to see if that could be used in West Yorkshire. And then another project was around the use of LoRaWAN long range wide area networks to kind of share information on flood hotspots and flood difficulties. And that's actually an ongoing project as well. So they're the two that I'm presenting on. Yeah, the first one was around looking at the use of flood early warning systems by communities. So again, these aren't kind of fully integrated models, but really trying to find where communities are using kind of flood warning information or their own. They might have worked with private sector providers to get monitoring on smaller rivers and tributaries, to see kind of how they use it, what successes they had and what difficulties that they face. And the aim was really to find if there's recommendations that could help communities in West Yorkshire. So we're quite open to see what communities we're using. It could be a mix of the formal EA flood warning systems that are publicly available and rain gauges, or developing their own private sector monitoring, or do they use flood guidance statements? Who is providing the information and who gets the information? So is it around flood wardens and flood groups or other charities, say, and what happens next in the local community, and picking up some of the challenges as well. So from this, we kind of identified 10 flood groups. They were all flood groups, mainly in Yorkshire and Lancashire, probably because we kind of went out from our own networks in Yorkshire. So it wasn't an exhaustive, systematic kind of survey of different flood groups. We found that they'd mainly developed in response to a flood in the local area. A lot of them had really good skills in the local community, retired engineers, hydrologists, professors, teachers and academics, IT experts. And then strong support in the early days around establishment from particularly the Environment Agency and other local councils. We found strong connections to parish councils as well, which gave them kind of credibility. But then challenges started creeping in, so mixed kind of continuous support from the Environment Agency, particularly where post-COVID, where contacts were lost, and then potentially as resource stresses kind of hit different government agencies. And then we found that also flood groups could be fragile, potentially relying on one or two key individuals, sometimes with caring responsibilities, in ill health, etc. So basically what we found was flood groups mainly operating in more rural areas and small towns. And then we plotted it against the indices of multiple deprivation and found that they were mainly in affluent areas. So probably not really news to a lot of people. So yeah, what we found was a mix of using EA local information, but also developing their own bespoke river level monitoring, rain gauges, working with private sector, where they could get funding, very kind of adaptive to trying to get funding from different sources. We found this dashboard produced by one of the flood groups, which we think is probably one of the best dashboards that we've come across in terms of the mix of different flood warning information from different gauges. So that was really impressive. And we found a lot of impressive kind of work out there. So Whalley and Billington had a video equipment on a trash screen, which they could monitor whether there was build-up which they needed to clear. They felt that that had stopped flooding in a few different cases, and they worked with a private sector provider on that. Aston Ingham, a very new group, had developed 3 monitors with a private company and met kind of monthly to review data, establish trigger points and explore what software they could use. Fish Lake, another small kind of community, but with 30 flood wardens and analysing a range of information as well. And then one in West Yorkshire, which is a strong network of flood groups and flood wardens across the Calder Valley. So yeah, and then we started picking up key challenges as well, around feeling like they've probably done as much as they can unless they got good flood defences, but they're often in small places. Declining contact in flood risk management agencies, and then issues around funding, insurance and litigation. They felt that there was hostility sometimes in the community and they were at risk of getting, say, taken to court or worse. And then also things like reliance on sandbags, and they could be fragile and lose support. So these were our kind of key recommendations, that we felt that working with flood early warning systems was a real opportunity to work with flood groups and kind of build up their capability and capacity, but also feedback from the flood groups what some of the flood risk management agencies could do better in this area as well, particularly around kind of technical support, placements of flood river level monitors and gauges, and then also working together so that they could understand the latest kind of modelling, nowcasting information that's, say, being presented today would be really great for flood groups to understand that a little bit more and potentially work together. So yeah, that's on that one. And then the second project was around the LoRaWAN project. So this was more working with local authorities and digital sensors to reduce the risk of surface water flooding, and in particular identifying flooding hotspots and reporting issues back so that there could be early warnings in the community. So yeah, surface water, obviously a growing problem. Response is reactive rather than proactive, but there is significant interest in the YFLIP programme. It's a regular point of discussion in the monthly monitoring meetings, road and gully monitoring, producing early warning signs, sharing information and learning from good practice examples. So this is one where they're really looking for kind of practical results to help the local community again. We got some funding from the government to explore the use of LoRaWAN. Is that a viable flood warning system? And can the information be shared across the 5 West Yorkshire local authorities? The answer from that was yes. That LoRaWAN's a kind of internationally recognised system, and a lot of local authorities are using LoRaWAN to share information on things like air pollution, crime, use of green space. A lot of local authorities are really looking at LoRaWAN as a way, a kind of cheap and affordable way of monitoring data and sharing information. And so from that pilot this year, we've got a formal kind of partnership with Wakefield to develop prototype surface water flood sensors in hotspot flooding locations with the sensor housing, and create a real-time kind of dashboard to share information. So firstly, to share information in Wakefield, and then see if we can develop a model across West Yorkshire. MapRain is one model, but that's only used by one of the local authorities. And then Pang Valley was a kind of dashboard that I showed earlier that looked like a good example. And then a continuous focus on data sharing and knowledge exchange within YFLIP. And that's kind of continuing as it goes on. So yeah, that's my final slide really. We've got a website, we've got our annual conference on the 24th of November, and we're producing a report on the flood warning systems and communities project. We are trying to write a paper. We've got a lot of good feedback, which is helping us think through our kind of recommendations and findings on that one. And then the LoRaWAN project, as I said, is ongoing. So that's me. Thank you.
Very much. Next, we have Callum Bow from ECMWF. It's worked as a scientist at the Hydrological Monitoring and Forecasting team at ECMWF in Reading for 10 years. He works on the forecasting of flash floods and flood inundation at European and global scales. Responsible for flash flood products which are produced and works with colleagues at the centre and the Joint Research Centre, the member states and universities. Callum.
Brilliant. Right. Thank you very much for the introduction, and thank you very much for the invitation to talk. So I'm Callum Ball. I'm from ECNWF. That's the European Centre for Medium Range Weather Forecasts. Bit of a long one. I work in the Reading office. We have offices in Bologna and Bonn as well. So I'm going to change the scale that we're looking at, going from the sort of very local. Now we're going to the pan-European. And I'm going to talk about the sort of flash flood forecasting efforts there through the Copernicus Emergency Management Service, CEMS, and the Union Civil Protection Mechanism. These are sort of European scale projects, and we do like a good long acronym. So just to also acknowledge contributions from umpteen colleagues at several institutions there, like both in ECNWF, the Joint Research Centre, which is part of the European Commission, and the Polytechnic University of Catalonia there at the bottom. So just there'll be sort of two parts to the talk. So the first bit, we'll talk about flash flood forecasting within CEMS. So this is EFAS, the European Flood Awareness System. Some of you may have already heard of this. So I'll just explain sort of what CEMS is, the overall framework, and what we do with the flash floods forecast in there. But then I'll go on to talk about a UCPM funded project called Inline. And what we really do here is use this as a test bed for trying to develop new pan-European flash flood forecasts. So it gives us like a test bed to try and fail sometimes to develop new things, and also really engage with users more frequently. That's something that in EFAS we've been a little bit top down and just imposing things. Now we want to get more interaction with users and allow more configurability from the user's side. So firstly, what is CEMS? I mean, we don't even know how to say it, because I, as an English person, say CEMS, speak to a French person, it's SEMS, Italian, it's CEMS, etc., etc. So yeah, it's part of the EU's Copernicus services. That's sort of Europe's Eyes on Earth, I think is how it's called. And there are 6 sort of main themes of Copernicus, which you can see up here. And the one of interest that I'll talk about today is on the bottom right, the emergency service there. And that itself has 5 components. So we talk about things like the early warning service, that's the EWS part of wildfires, floods, I think this laser pointer is dying, and droughts. And I'm going to talk specifically about floods there. So this is about the early prediction of floods. So we have this consortium to run this service about the early prediction of floods. It's led at the top there by the Joint Research Centre. They're the entrusted entity to make sure that the service runs. And you can see that there are, at the bottom here, there are several organisations involved in different aspects of this. The main one that we're going to talk about today is what we do at ECNWF, which is on the bottom left. We're what's called the computational centre. Basically, we have the code, we have the weather forecast, we have a big supercomputer, and we produce the forecasts that go on the website. That's our role. There are other centres there who are like the dissemination centre. They're the ones responsible for sending warnings out to EFAS partners. We have hydrological and meteorological data centres there who are responsible for collecting hydrological observations, meteorological observations, which are used to initialise the forecast, but also to evaluate and calibrate the models as well. So what is EFAS? It is a European flood awareness system. There is a global version of this as well, but I will just talk about the European flood awareness system for today. It is a pan-European flood forecasting system which produces forecasts twice a day of stream flow, and it's basically highlighting areas at risk of flooding. And it runs a gridded hydrological model called ListFlood, runs at 1 arc-minute spatial resolution, and what it does is it obviously produces its discharge forecasts, and it then can produce a nice cluster of reporting points, as you can see in the middle there. That's for Storm Boris. So the purple would be where there's a chance of exceeding the 20-year return period, and so on. So it's really quite good at highlighting areas at risk. The forecasts for the first 30 days after it's been produced are only available to EFAS partners. Those are typically hydrometeorological or civil protection agencies. So for example, like the Flood Forecast Centre here in the UK is an EFAS partner, so they would be the only ones to be able to access it. The reason we do that is a sort of one voice principle. We don't want to be putting something out there publicly that might actually clash with what's been put out by the national authorities. So that's the reason behind that. But after the 30-day embargo, things are publicly available, so you can anyone can go and check. So why do we do this? Why do we want to have a pan-European system? You know, especially now that many countries have their own systems. Basically, it's for sort of three main reasons there. We're supporting preparatory measures before, particularly major events like Storm Boris, for example. It's also important to have consistent information across Europe. Some countries maybe still don't have their own forecast system, and where forecast systems are available, they're not comparable between different countries, which can be a bit of a problem if they're sharing a water course. So the European Commission might want to know how bad a flood is going to be, but if there's different forecast systems which have different return periods, thresholds, etc., it can be quite difficult. So this gives a consistent way of quickly seeing what might happen. And then we're not trying to ride roughshod over anyone at the national or local level. This is meant to be complementary. They check EFAS and see if there's agreement there, which might give them more confidence going ahead. So specifically, what do we do about flash floods forecasting in EFAS? So just to start with, what we talk about flash floods here is actually riverine flash floods. There's nothing yet at the moment about surface water. That is something that comes in the inline project, but I don't have time to talk about it today. And so what we're talking about riverine floods are the sort of rapidly responding catchments, so to speak. And we're defining this as any catchment that has a drainage area of less than 1,000 square kilometres and a response time of less than 24 hours. So that's a pretty broad definition there. And the methods or the index that we have is called ERIC, the European Runoff Index based on climatology. We did actually have a corresponding indicator based on radar that we called ERICA. So that was quite nice, but we retired her a few years ago, and we are in the process of trying to retire ERIC as well, because it's quite old. It's been in EFAS since 2015. In fact, my first job was putting this operationally into EFAS. So the way that we produce the forecast, just to go on the bottom line here, so we take a limited area model, that's Cosmoleps, that has forecast twice a day. We put that into a hydrological model called ListFlood, which gives us surface runoff forecasts at 1 arcminute. These are at 6-hour time steps going out to 5 days lead time. We then, at each of those 1 arcminute grid cells between less than 1,000 square kilometers drainage area, we accumulate the surface runoff in periods of 6, 12, and 24 hours, so rolling windows. And we compare those accumulations against the mean annual maximum that comes from the 20-year climatology that we have. And that comes from a model reforecast climatology. And where we exceed those mean annual maximum thresholds, we produce a flash floods point at that given location. We repeat that everywhere. So how does the product end up looking? So it ends up looking a bit like this, where you've got firstly like reporting points. These are the small triangles. I don't know if you can see, sorry, the laser's dying on me. But basically, if you go up to the coast here, you'll see small inverted triangles. And what I use, those highlight areas on the river where we say there's a risk of flash flooding. So a user can click on that point, bring up the hydrograph that you see on the bottom left there. So where you go above so the red is exceeding the 5-year return period, again from the model climatology, and the purple is exceeding the 20-year return period. So you can see in this case, actually, only a few, the sort of upper part of the ensemble has a risk of going above the 5-year return period. Then those sort of colored pixels that you've got coming sort of down from the reporting points, those are the river segments upstream of the reporting points, which we say are at risk, where there's a risk of flash flooding happening. So the purple is where there's a risk of something related to the 20-year return period, red somewhere around the 5-year return period. And what we do is we also send out notifications to partners if certain criteria are met. So if there's a greater than 30% probability of exceeding the 5-year return periods with less than 48 hours lead time in these small catchments, then we issue a flash flood notification that goes to the relevant partner in that area. So this is an example for Sweden, and it just gives a quick summary of which rivers are affected, the exceedance probabilities, and when the peak is expected. But we know that there are several limitations on this. So this is all based on NWP. We know that that has a huge limitation when it comes to convective events. There's no link to potential impacts. So we can often with an NWP, all we can do is highlight quite broad areas. Users want to come back and say, okay, well, where's most at risk within those? And as I said as well, this is a very top-down approach. We have one rule for everyone, but everyone has different needs in terms of what thresholds they might like, what tolerance they have to false alarms, etc. And we only have interactions with users via EFAS sort of once a year. They can provide feedback on the fly with responses to notifications, but it would be nice to have something more regular. And this is where this inline project comes in. which is funded by the Union Civil Protection Mechanism. It's a 2-year project, which is led by the Polytechnic University of Catalonia. And what this is doing is it's trying to solve most of those limitations that I've highlighted previously. So we integrate radar data that come from the Opera composite. So it's pan-European, well, mostly pan-European. And we blend that with the ECNWF IFS ensemble to produce forecasts every hour that go up to a lead time of 5 days. So what we have is nowcasted precipitation. So for the first 6 hours, that's a blend of the radar and the NWP. So as we go further towards that 6-hour lead time range, we're going to be using mostly NWP because we trust the radar nowcast less. And then after 7 hours, it's based entirely on the ECNWF IFS. And then what we do is we put that into a flash flood indicator similar to ERIC. It's actually a precursor called EPIC because it's based on precipitation rather than runoff. And that's what you get here on these sort of red and orange highlighted catchments. So what we do is we accumulate that rainfall on the river channel network, see where it exceeds the climatology-based thresholds. But then what we do is overlay that onto a map of exposure, which relates to like population, critical infrastructure. These come from pan-European data sets. So again, there's limitations there. And we sort of code things according to an impact matrix, which you can see on the top there. So on the top right. So you've got on the y-axis the probability of exceeding, so the 2-year return period, and on the x-axis is the potential exposure, so whether a lot of people live there or not. So another thing that we're trying to do in the project is allow users to specify and configure their own criteria for how they receive notifications. So they can access like a simple web form like this, where they can specify exactly what products they wish to receive notifications for, the lead times, what impact levels, so if they only want sort of red or above, and specify their area of interest as well. When something then does meet their criteria, they'll receive an email that might look something like this, which obviously the map is just their area of interest. It shows the rainfall, etc. Thank you. And then the table at the bottom highlights, say, the administration regions where there's the potential impacts there, and again, shaded by the sort of warning level. And the other thing that we're trying to do here to have more engagement with users throughout is develop a community of interest. So this is, we've established it, and we had our first meeting a couple of weeks ago, and we've had over 60 institutions from over 21 countries across Europe, which are shown in the blue there. And these are mostly from civil protection authorities and hydrometeorological agencies. And the idea is that we're promoting what we're doing in the Inline project, but we really want their feedback. We want them to tell us, okay, well, we don't like how the products look, or why are you using this threshold? And we also want, many of them are involved in their own projects to develop their own national warning system. So we really want to hear those kind of stories as well and learn how we can complement it. You know, we might get ideas from them, but we also learn what data they might need from us. So one of the things we want to look at is whether we make our forecast data available, which then they can integrate directly into their own systems and say, overlay with their own exposure data. So then that means it's much easier for them to configure things and integrate it into their own warning system. So we try and meet every 6 weeks. I actually need to start planning the next one. So we have an interactive feedback session. I try and give them homework each time and say, please, can you go and look at this and then give me feedback. And then we have a more sort of, we call it a deep dive, but it's me sort of talking via PowerPoint for say 40 minutes or so, trying to explain in more detail how we make some of the products. So that was everything. Just to leave up some conclusion slides. So EFAS, we're producing twice daily pan-European flash flood forecasts. We have this one rule for them all about issuing notifications, but in Inline, this project, we're trying to develop sort of nowcasts, which are driven by radar observation, so we can update more frequently in rapidly evolving situations. We're trying to introduce more user configurability, engage more frequently with the users. And one thing I haven't mentioned is that any developments that we have in Inline that we like go into EFAS, so then they can become operational and improve the service. So thank you, and yeah, well, any questions later, I think.
So it's a forum for people to ask questions of any of the last speakers from the last session covering policy and that. And governance and interventions. Can I ask for questions?
Can I ask a very general question? How do you define a flash flood and how do you distinguish it from something that is a normal flood? I found that so many definitions, you have nearly as many definitions for a flash flood as there are flood hydrologists.
Who would like? Who would like to be first on that?
I avoided the words flash flood on my presentation. So,
Thanks for the hot potato. We don't have in speaking from the insurance world at least, there isn't a specific definition necessarily of flash flood as in terms of how it's characterized and how it may be excluded from a policy necessarily. So you remember I was talking about the Norwegian sort of national pool that might exclude pluvial flooding. That would incorporate flash flooding, but they wouldn't necessarily segregate out flash flooding as an item. So yeah, I think you probably could ask 50 hydrologists here for a definition of flash flooding and get 50 different answers, couldn't you? But I don't know if anybody has a definition they want to share.
If we can.
Thank you. I wanted to ask a question because we heard quite a lot about local predictions and local, like from Yorkshire, from catchment area, etc. How is that linked to the main national forecast that's given out? I mean, is there any feedback loop?
yeah, so that was one of the, so we've produced a paper from our work and in draft stage, and that was one of the questions from the reviewers, was that feedback. So at the moment there isn't from, say, local authorities or flood groups, but I think we were trying to think of a recommendation of if, say, the Environment Agency could work with flood groups on, and the Met Office as well, on kind of latest initiatives around nowcasting. That would be a good point for discussion around how to feed back their information back up the chain. But I feel like they would feel less confident that that was going to help at a national level, and really they're just focusing on their own local level and seeing how that could help them there.
Can I just follow that up? I mean, I was just going to ask Stephen, I mean, presumably there is some knowledge there. Is this on? There's some knowledge that sits nationally, which you could utilize to actually even improve the local forecast.
And don't get me wrong, when producing forecasts, well, myself in particular, I do follow a lot of local groups, including your own, to increase my awareness about what's actually going on the ground. For Somerset Levels, again, has a lot of local information, and getting that feedback, it does help drive the national story.
I was going to provide a slightly different perspective on the question. I know your question was around forecasting, but I think in the context of more sort of longer term flood risk, we very much do engage with users and get feedback. So in the work that was presented earlier today, in a future flood, for example, we are providing new estimates of flood risk and new understanding. So then the question is, how important is that for users? And at what point do they adjust their methods? Obviously, there needs to be sufficient impact in order to update and overhaul things. So we are working very closely with people, and will do increasingly as the project develops. So, for example, we have working with the Department of Education to understand exposure to schools and infrastructure, and understanding how differences in the flood estimates, what impact that would have. And it's an important part of us developing the work that we're doing to understand, where the appropriate points to feed into the flood risk cycles are, and how people can adjust the methods that they're currently using, if necessary.
Sorry. So can I just take that a step further? So presumably there's quite a big gap between the product and the users. And I know you talked about education. So is it an ongoing process to educate the users of the product? Because every user will have a different need for different purposes. And how is the industry actually taking this forward to help users educate themselves to better use the information that's predicted?
Yeah, I mean, this is a real challenge. You know, we don't have the capacity to work with every single individual and every single application to tailor information. But I guess what we're trying to do is we're trying to identify maybe some key case studies where we demonstrate the value of new information or the importance that it might have, and also take feedback in terms of processes that we're doing or decisions that we make. For example, you know, how far into the future do we look? What scenarios do we do? You know, there are key decisions we make throughout the production of information, and we need users to feed into that. So we try, certainly within the UK climate predictions process, we're now updating the whole new set of projections, and it's now going to be UKCI, UK climate information, very much with a massive user angle. But yeah, we're grappling with this because, you know, we don't have the capacity to interact with every single use case, but hopefully through identifying some key ones and working closely. So within the Future Flood, we're working closely with the Environment Agency and Bristol City Council, then we can develop some use cases that are applicable more widely.
I mean, for me, it was refreshing to see from, sorry, I forgot your name. Yeah, that they're working very closely with the customers. The reason I'm asking is I come from the energy industry, and going back 15 years when the whole process started, there was no connection between the users and the output. So it's very refreshing to see what was happening.
I would just say that we have the benefit of working with a very well-defined set of users. So we know exactly who our users are, and we have an ongoing engagement with them. So, which is quite, that's a bit of a luxury, and for many user groups, they're not that easily identifiable or easy to access.
Any other questions?
I related to the presentation on Mozambique. The kind of the long-term projections of hurricane tracks. How does that? How do you translate that into improving the early warning systems with the local Met offices in Southern Africa or Madagascar or Mozambique? Is the information and the modeling that you're doing resulting in better projection of the direction of travel or the impact, or yeah?
Okay, so the National Met Services are actually partners on the project and are working closely with us. So, for example, one of the figures I showed a southward shift. You may have seen it in terms of the shift in Category 5 tropical cyclones. So, you know, that is then, we're in the case where tropical cyclones are hitting a part of Mozambique where people have no experience actually of ever having had a tropical cyclone. So they've seen it on the television in terms of people being impacted in the north of the country. So, I mean, one of the first things we're doing is working with people in terms of drills so that people actually become familiar and understand, you know, what it would mean so that they are prepared. So when, you know, these predictions, if they come to fruition, people aren't completely caught out of unawares. So there's issues around new regions being impacted that have never been before. There's also these issues around storms being a lot more intense and maybe developing more quickly. I think, again, it's a case of, obviously, we need to strengthen the systems that they already have, but having at least awareness of that helps with maybe some of the financing needed towards strengthening the systems in the countries?
I have two questions about the European storms sorry about my voice, in 2021. Was it a failure because of the large-scale and regional predictions? That was the first question, or the preparedness. And I read many of the reports about the reviews afterwards. And there were a few storms 100 years ago which actually were as strong, or almost as strong as Bernd. Have the lessons been learned, and are people still implementing the lessons?
I think that's a good point, and that's kind of why there was such a reaction from the insurance and reinsurance markets to that 2021 event, was that it revealed really that although the kind of meteorological analysis of that event showed, as you said, that it wasn't unprecedented, that's not a 1 in 1,000 year return period event, is something in the order of 1 in 50, 1 in 75, and we've witnessed it historically. What was unexpected about the event was the scale of the losses, and that was where the catastrophe models, or maybe the prediction, the preparedness had failed. So it's the whole chain through the catastrophe models, that although maybe they were getting that hazard component correct, and possibly there would be events within that catastrophe model that were fairly well reflective of what happened from a hazard perspective, but they were simply not producing the losses that were actually seen through that event. And that's because of the characteristics of that event, the preparedness, the lack of preparedness that you'd mentioned, but also the probably increased vulnerability of those assets that were hit relative to the understanding and the expectation. And so that's why probably since then there's been a movement across many models and certainly insurers and reinsurers to kind of adjust upwards in terms of their loss expectations for that style of event. But I don't think it was the case that anybody would be talking about that event as unprecedented from a meteorological or hydrological perspective. But certainly the preparedness is something that we see all the time as a big factor in losses overall. And that was even more so the case probably in the 2024 Valencia event, where that really was a failure of warning. And that's probably not too controversial to say that. And there's been a lot of criticism, hasn't there, of the Spanish sort of meteor service. Even a BBC documentary, I think, that looked at that too. And there were failings throughout the chain there. And had they been able to get proper warnings to people, there probably would have been a difference in not only the loss of lives, but the damage caused too. So I think that event probably is more representative of a failure of preparedness than the 2021 one, which was more about the vulnerability.
He passed you on 2021.
Oh, I might as well stand here. That's a long way back now. I can't remember off the top. Sorry, I'm going to be very neutral. We have to be. No, I'm not going to say it. I think we're on a forecaster project called Aristotle, where we take it in turns to look at FAS and also national warning services, and give a heads up to the European Commission about these events. So things like the R Valley, but also Valencia. And I remember for the R that there was a lot of uncertainty, but what you could see is the real extreme tails of the ensemble forecast, even a few days out, were hitting like the top that we've ever simulated in our 20-year hindcast series. So in hindsight, you can look back and say, oh, should this have given us a heads up? I'm not in any way claiming that this was some kind of good forecast, but we need to look back at some of these events and think, are there different ways that we can interpret the forecasts that maybe can just give a heads up? That's sometimes we may be really going to top at if you look at the extreme distributions of the ensemble, maybe there's something there that you just need to give a heads up. It's not you're asking people to evacuate their houses, but is there just something there that maybe we should just pay a bit more attention? It's something that I'm working on a project at the minute, and this is something I'm just trying to tease out. Like, is there actually anything in the ensemble, or are you just going to get drowned in false alarms? So it's difficult, and there's nothing much we could have offered, unfortunately, in that. that particular case.
Thank you. I have another question related to the CAT model for Sam, really. So you mentioned that, the CAT model obviously is for the large scale global or the whole European scale, and then lack of, I think capability to look at the details. I just wonder, in this domain, whether there's any attempt to embed different models. For example, you said, I think the CAT model can really identify those kind of hotspots or, region that could potentially, more at risk of flash flooding. And then whether you can, for example, embed this kind of detail model and then look at the detail, I think impact of potential flash flood in those areas to give you a better information to calculate loss or something.
Yeah, it's a nice idea, and certainly on the whole, when you, as a user, when you purchase a CAT model, the hazard of course comes fixed to you. It's not as if you're purchasing a two-flow or an Innovyze license and building your hazard. It comes to you broadly fixed. There's some things that you can tweak as a user, but mostly the hazard there is fixed. But there is some flexibility with some model vendors where you can upload, for example, your own footprints or your own underlying base mapping. So although to my knowledge that's not widely used, I think what you're saying is absolutely possible, where in some model setups where you would have underlying base maps and an event set that would then kind of bring a mosaic of an event. So at this observation point, it calls the 100-year flood map. At the following, it calls the 50-year flood map, etc. You could replace those underlying flood maps with those of more detail should you have them available potentially. And yeah, although it's broad scale, as we discussed, we are seeing some even global CAT models potentially with resolutions of sort of 5 meters or 30 meters. So it's not necessarily at the extreme detail that you showed earlier, and that we're seeing in other industries. But I think it's getting there, and from a hazard side, those models are catching up. What I would say though is that it's probably from a hazard perspective within these CAT models, that's maybe the area that, just my opinion, but that's maybe the area of kind of least concern in the CAT modeling chain from an uncertainty perspective. The hazard obviously is important, but the vulnerability is something like a finger in the air, really. It's a bit of a guess. There's so little evidence. It ranges so much. You can have two properties next to each other experiencing the same flood depth, but one produces 20% damage and one barely anything. It's so varying that component of the model is probably where we would like to focus were there more information available. But certainly what I think you're saying is plausible.
Thank you. It's kind of on the same topic as sorry, you're getting the questions, but I was wondering, with these models, you're talking about forecasting hazards, but and you've just talked about the fact that you can have two properties side by side and they can have very different damage. Is the insurance industry doing much to actually encourage people to reduce the costs overall for claiming? So, is there much encouragement? We talked about sandbags, but to be honest, that's a bit of a band-aid in most situations. It makes people feel good, but the actual help that it provides in a lot of situations we're seeing with models, it varies quite a lot. Is there much that's being done to maybe, for these places that have been identified as high risk, to, make sure that these houses can maybe bounce back faster, therefore cost less money to the insurance industry?
Yes, that's a good point, and the one that springs to mind that's obvious for the UK at least is the Flood Re scheme and their Build Back Better scheme, which many will be aware of. So that in that instance, insurers that are signed up to the Flood Re scheme and where the property has had a flood event can apply for, I think it's up to kind of £10,000 in funding to make their home more resilient in some way, be that through resilience measures or protective measures to bounce back faster or to prevent the future flooding instance. So those kind of schemes are coming up, and that's obviously part of a transition plan for Flood Re, how they might in future exit a market is by trying to make the whole insurable market more resilient in general. Unfortunately, we just don't see a lot of necessarily huge take up on those sorts of schemes. And certainly when I worked in engineering consultancy, we saw similar, where for local councils we might be doing sort of pluvial modelling and potentially offering to homeowners property level flood protection where they've been identified through the model as being at high risk. The take-up rate is absolutely appalling, and I think it's partially that do people want to advertise their house as being at risk of flooding? I'm not sure. Do people trust the models well enough to say I'm going to get a floodgate across my house, even though I've never necessarily experienced flooding myself? I think it's all of those things. But yeah, that's the obvious one to me is the flood re-scheme, and I think it's picking up momentum a little bit. And I think there was a comment earlier that maybe we don't flood enough in the UK, and then maybe if you do, then the take up might be better. But that's definitely a struggle.
Yeah, thank you.
Thank you. Following questions on CAT modeling, maybe this is trivial. So do we have a publicly available inventory of damages and claims from the storms and flooding in UK that academic partners could study? That's number one. And number two, is there some generic CAT model that will be also available to academic community?
For number one, for UK specifically, not to my knowledge. There's some resources on sort of damage functions that are built up through the academic community and through the so things like the multicolored manual, which I think is partially from Loughborough Uni, and the Joint Research Committee have got some damage functions, etc. But in terms of a database itself of claims that are tied to hazard, it doesn't really exist, and that's kind of why building up flood vulnerability is so difficult. Following a wind event, for example, you'll receive as an insurer the claims and know a value for the damages incurred, and because, as I showed, you'll get a very good footprint for that. You can associate the hazard with the damage that you've received in that peril. In flood, you're just not going to get that. So very, very often when there's an adjuster or a claims staff out assessing a claim, you may not ever record the peak hazard that was incurred. You're just getting an idea of the losses. So we just don't have that database really of hazard associated with the loss, and that's where it's missing. I think there's better detail available through FEMA, so American losses that are partially tied to hazard and with a measure of kind of loss as a proportion of the insured sum. But from a UK perspective, I think not. In terms of a open source CAT model, there's certainly open source platforms, but whether there's a free to use CAT model itself, I'm not sure. Yeah.
I think that needs to draw it to a close now. Thank you. Can I ask everybody to thank our panel again? And it just leaves me to draw the meeting to a close now. I want to say thank you again to all of our speakers today. I also want to say thank you to everybody for coming today. Look out for next events, and look out for on the Royal Met Soc and also on the British Hydrological Society's website, and look out for the new BHS website as well, which is coming soon. If I can ask everybody to hand in their badges, I'm assuming Catherine. I want to say thanks to Catherine and also to Will for helping organise today. And I'll just check there isn't another. There is another slide about future events, so do keep an eye. The talks from today will be provided and on the website, so have a look out for those. Thank you for coming, everybody, and safe trip home to everyone. Thank you.
How you doing?
Thank you, everyone. We do need to be out. I'm sorry if you're asking any questions. I wanted to ask you about